I didn't even have to ask you to clap. Please clap. Good. You sound kind of tired. I'm not. I just had a ton of coffee. I'd like to start today off with a couple corrections to some previously shared information. First, yesterday, I announced that it was Tuesday. That's no longer correct. Sorry. Also, the weather has been totally incorrect Monday and Tuesday, and we regret that error. It's now fixed. It's a little chillier, so I can welcome you to Portland. Welcome. Also, the Oregon Zoo closes at 6, not at 5. Also, the cute pigs are only visible between 10 and 1. So, think about that. Fourth, Adobe Acrobat is easier to full screen by pressing Command L. So, I know that now. Also, you may have forgotten to pick up socks. It's not too late to pick up socks. You may also have forgotten to pick up a donut, thanks to Librato. It is probably not too late to pick up a donut, thanks to Librato. So, think about that. Also, you may have forgotten to check out our Platinum sponsors who are upstairs. Many of them have TVs and cool setups. It's almost certainly not too late to check them out. So do that. Today is Michael Gorsuch's birthday. Happy birthday. And then also in past years, today has been workshops. We regret that error, and we will just be continuing awesome talks all day today. So sorry about that. To get us started with awesome talks, we have Justin from Netflix. Come on out, Justin.
All right, there we go. Hi, my name is Justin Reynolds. I'm a senior software engineer on the traffic and chaos team at Netflix. And my job on the team is to help the traffic and chaos sides both understand the impact of what they're doing. Because we're purposely affecting millions of users, we need live feedback on our hundreds of microservices. Why is this so hard? Why can't we use dashboards? Why can't we just set up alerts? It's a little difficult while we're affecting millions of users in real time. We can't wait for an alert to fire. Most standard visualizations are not meant to be stared at in real time. They're meant to be more something has happened. Let's go look, investigate, and figure out what happened and what time it started. So we needed a way to feel, a way to intuit what was going on while we were performing traffic failovers or chaos exercises. And on our team, we like to call this intuition engineering. And I'd like to show you our first foray into the idea of intuition engineering with our tool that we called Visceral. First, talk about the why. I'm going to go through a little bit of the Netflix history and failovers. I'm going to simplify it quite a bit, because that's not what this presentation is really about. If you want more information about that, Luke Kosevsky from my team gave a great talk at QCon New York, and that video should be online. If you want to know a lot about this. Long time ago, Netflix moved out of a data center into AWS, into a single region, US East 1, and as we grew, we moved into a second region, EU West 1. This was going great, and we now had a story for our global users, but they were siloed regions in that users that were being served out of EU West could not be served out of US East and vice versa. Which was all great, it was fine, until the great ELB outage of 2012, where most of Netflix was down for our US, Canada, and Latin America users for an extended period of time. This was not a good experience because it was mostly outside of our control. We felt pretty helpless, nothing we could really do to save our users. It wasn't possible to serve users out of the other region because they were siloed regions. So this started our process of regional resiliency. So after many long hours and a lot of work, Netflix launched in a third Amazon region, US West 2, and this was different. US West 2 and US East 1 shared data. So users that were served out of US East 1 could also be served out of US West 2 and vice versa. And even more recently, after a lot more work, we made great progress with Global Cloud. Now all of our users can be served out of any region. So if we have a region that goes unhealthy because of Amazon or because of something we did, we can move users to the 2 other healthy regions. There's a little bit of complexity to moving users. Within each region, we run pretty lean to save on cost. We don't run a bunch of extra capacity just waiting for extra users to come in. We run a little bit of overhead just in case, but definitely not enough to serve all of Netflix from 1 or 2 regions. So when we are about to perform a failover, we need to scale up the region to be able to take more traffic. And there's a little bit of art to this. We can't just hit scale up and then immediately send all the users there because it won't be ready to take the users. And then it'll end up effectively knocking over the healthy regions that we're trying to send the users to. If we scale up too slowly and send users too slowly, our users are having a lot more pain than they need to have because there is room in the healthy regions for them to be served, and our whole goal is to alleviate customer pain. The reason this is difficult is we run a system of many microservices, all communicating. Very, very difficult to understand the health and ability to receive traffic of over 200 microservices. When we're doing a failover, we need to answer the question, is the region ready for more traffic? How can we do that? Like I said, it's pretty complicated with this in one region. Imagine when we're failing the 2 different regions. Take this and multiply by 2 and try to just look at this and feel, and look at dashboards and alerts and try to get a feel for if it can take more traffic. This is a standard dashboard that I've created and we still use this is the traffic entering into Netflix from the internet in each of the 3 regions, and all of the traffic being proxied between all 3 regions. It's very useful for doing research after something went wrong. If we get paged, we can go look at the dashboard and see what happened and where it happened. We can go look at the dashboard. But again, for our use case, we need to know now. This provides lots of extra information for our use case. The line charts do show change, but we are affecting most of that change on purpose. So it's hard to reason about what change is the bad change, what indicates that we're doing something wrong or need to stop what we're doing. So this is the now of the dashboard. This is the far right of the graphs shows what's happening right now, and then the other boxes down there show current value. And if we're in the middle of affecting millions of customers, moving them around, this takes way too long to scan all these graphs and look at all these current values and see if they kind of make sense. This gets even more complicated when looking at the services within a region. This is just a subset of the regional services and some level of health about the services. How do you reason about this? What's the most important? There's some that have red. Are those really important to the user experience? We can't really tell from the way this is laid out. We could sort it by traffic. Obviously, it's probably that the services that are taking most traffic are probably most important, but what about our logging service? That probably takes more traffic than most, and if that falls over, it shouldn't affect the users, which that'd make a good chaos exercise, shutting down our logging service. But way to get a better understanding for if it can take more traffic is seeing how it fits within the infrastructure, within the request path for the user, which this doesn't give us. So we need to be able to reason about getting a gut feeling for if a service is important to the streaming experience, and if the health of that service matters for when we move traffic. So we did a little bit of exploration. We wanted some out-of-the-box thinking because the standard visualizations weren't helping, so we came up with the crazy idea of the pain suit to start the out-of-the-box thinking. The idea is that when we're performing a traffic failover, we'd wear a suit covered in electrodes that would send jolts of pain through your body if services started to become unhealthy. And services that were important, like our proxy layer, the electrode would be over your heart. So if you started to have heart pain, you'd know that there's something wrong with our proxy service, and some like user image service would be on your pinky finger. So if that started hurting, who cares? It's a pretty ridiculous example. but it really got us thinking outside the box. What could we do that does provide more of an intuition and a gut feeling for the state of the system? So we started exploring a little bit more. We went through the feel, so started going through all the senses, kept going down some crazy paths. What if we could smell the health of a region? The account service stinks. What does the smell mean? We don't even know how to reason about that. What about taste? How can you generate taste? Can you convince engineers to taste something all day until it tastes bad? So quickly we decided to use a visualization. It's something we're all conditioned to understand. Lots and lots of research studies show that it's easy to reason about. Color theory, image theory, there's a lot of research about how to build something that is easy to grok visually. So starting there, we went through all the standard graphs, line graphs, bar charts. All of these have some downsides for our use case. Most of them are focused on change over time, exact number values, or comparison between values. None of those are important to us. We just care, can we move more traffic? Exact numbers don't matter. There's nothing to compare it to. And we don't care what exactly has changed over time, because like I said, we've caused most of that change. We care about understanding the current state of the system holistically. Let me show you a little bit of what we built. This is visceral. In this view, this is the global view. We have the 3 regions that we have in Amazon, and it shows the traffic flow from the internet going into each of the regions. The volume is really easy to reason. You can quickly tell that in this example with sample data, that US West 2 is taking most of the traffic, US East 1 is taking a little bit less, and the EU West falling behind. All of those dots represent some percentage of traffic flowing into the region. It's not a 1-to-1 ratio, because at our scale, 1-to-1, they would just be a massive wall that you couldn't understand. The dots that are the bluish-white are normal. A lot of color theory went into this about colors that feel nice and happy. There's some dots that are yellow that indicate that there was a response that resulted in a degraded experience, that the user still got a response, but it wasn't exactly what we expected. And then there's some red dots that indicate errors. Some level of errors is normal, probably served with retries. And one thing that we really like about this is immediately we got a gut feel, this looks fine. There's nothing really to worry about, everything looks good. And this is even interesting. Once Netflix expands more and launches in other regions, this scales well. At a 4th, a 5th, a 6th, it'll still be just as easy to understand. Where with the dashboard, right now this has 9 connections, the 3 incoming connections, the 2 proxying connections between each region. So if you're adding more regions, you start getting into like 16 graphs. 25 graphs, and at that point, that's way too hard to just stare at those graphs and understand anything. If you think about this region, something's going on, you want to go look into it, you can drill in. And this is showing all the traffic flowing between our microservices. This is just these are randomly renamed, so to not give away any secrets. But this is just showing all the services in our request path for what the user sees. The far left is the traffic. It represents the internet and has traffic flowing in from the internet to all of our proxies. Follows kind of the same idea as the regional view. There's circular nodes, lanes of traffic flowing between all of them. Dot coloring is the same. As far as the layout goes, this is a custom layout. Still needs a lot of work. There's a lot of mess going on with some connections that don't need to overlap. But we started with a lot of the standard layouts. Most of them did not work for our use case. They either focus on clustering close nodes, which is very good for like a social graph and seeing who's connected to who. That didn't help with the intuition side of it, where which services are important. The other focus of a lot of layout algorithms is to not overlap connections, which, as I said, we want to not overlap connections, but not at the expense of the request path. which internet starts here, then it goes to the proxies, and this is laid out from traffic coming in all the way to the edge nodes on the far right. Even with how bad this layout still is, it was still better than anything we had tried before, and it still gave us a really good understanding of the traffic flowing through our ecosystem as a whole. It's easy to quickly notice if something is weird. The nodes also get colored, as you can see down here. This one is red, which we use the coloring on the nodes for actual node health, which keeping in mind, this is a node at the edge, probably not as important, not too much traffic flowing to it. Might not have to look at it, so if there was something more red and focused over here, we'd start here. But since this is the only red one, maybe we can go and look at this. If you click on it, kind of dims out everything, focuses the node, and we now have this contextual panel, which right now it just has a tabular view of the connections. And this one says this is getting 97% error returned, so probably should go talk to that service owner and ask what's going on. We're leaving room here for we're going to add graphs. So this is where standard graphs come into play. You already have figured out which service that you want to look at from this view, following all the traffic. Now we can get into adding standard graphs, links out to dashboards, all the tools we all know and love. Then there's even a third view, which is the least built out, where you can focus in on the node. Get rid of all the noise, focus on upstream and downstream dependencies. This is really important for us when doing CAS exercises and introducing errors in this service itself, and see how it is affecting traffic flowing into it and the responses and all of its downstream dependencies. This view, we are currently undergoing a re-architecture redesign that I'm pretty excited about that will make this a lot more useful and provide a lot more context. But even still in this very simple place, it's already proved very useful during our CAS exercises. How did we get here? We knew we wanted to do visualization, so we started with a D3, where I think most people start. It's really powerful. It probably could have worked. I couldn't figure out half of it. It does provide a lot of client-side transformations, which when we're doing real-time, rendering real-time data, we want to do as little client-side math as possible. And it seemed pretty focused on the standard visualization types, where it is focused on change over time or showing visualizing exact values. So we decided we want to use WebGL to get the performance for the real-time data. Starting WebGL, we wanted the library on top of it to make it easier. Started with Pixel.js because it was a 2D library, but it's focused on Flash, and I worked at Adobe for 7 years. I'm done with anything dealing with Flash. So I quickly got off that one, settled on 3JS. It's a very good, very, very good WebGL library that gives you all the power you want without any of the complexities of WebGL directly, but still allows you to optimize down to the WebGL level if you want to. As far as the backend for our data, spun up a Node.js server because it's quick and easy. I know JavaScript. We use SALP, which is our request tracing system based off of Google's Dapper white paper. That's how we build our dependency graph. And then Atlas, which is our metrics and telemetry tool that is also open source. And we just take all the SALP data, all the Atlas data, do some combinations and basic stats, and generate the needed JSON for the UI. So this is a quick 90-second demo of us performing a split failover, fixing an issue, and sending the traffic back to the region. I wish it could only take 90 seconds, but if I showed you a video of how long it actually took, we'd be here for a while. First, there's normal traffic. There's traffic flowing in and out of the regions, and as you'll see, I believe it's US East 1, we'll start getting errors. Errors are going up, notice changing colors. So we're starting to scale the other two regions because we notice there's problems only in one region. And then we decide, once we're at a certain scaling level, we can start to proxy some of the traffic out of US East 1 into the 2 healthy regions. And this is the part where the scale up is important. Only send traffic if the regions can take it, and send it over as fast as you can into the healthy regions. And then as soon as we've proxied 100% of the traffic, the regions are able to take all of the traffic. We flip DNS to send all of the traffic directly to those regions. There it is. So now all the traffic is, thank you. All the traffic's going to the 2 healthy regions. We're fixing US East 1. US East 1 is fixed. Send all the traffic back to US East 1, but keep proxying on, so we don't overwhelm US East 1, and then slowly dial proxying back. So it can take traffic gradually, and then eventually we get back to normal state, where all of the traffic is back to normal, and we have fixed the problem and saved customers lots of pain. This point of view has already proven very useful in catching problematic states during failover before we affected customers. It gives us a better feel for the inner workings of a failover and how traffic is actually moving. Yes, we know we're proxying traffic. Yes, we know we're flipping DNS. But being able to see it in real time and what is affected by the changes we're making has given us the ability to make much quicker decisions and help customers much faster. Even with building this tool only with failovers in mind, it's already proven useful for our incident response team during incidences, migration efforts, and even our onboarding education, helping new hires understand how our system works. And other people use these videos at their talks at other conferences to help explain our complex architecture. With all that in mind, we have open sourced the UI component. It just takes a standard JSON structure. Just got to build backend based on your data and transform it into the JSON structure and send it to the UI, and you can have the same experience. We believe and hope that there's many other infrastructures and companies and metric systems that would be able to use this and have as much success with it as we have. There's still definitely a ton of work to do. The layout algorithm that I need to work on, make it pluggable so we can have other layout algorithms, the rewriting of that third view, adding other views, layering support, history playback. There's a huge list of features that we're going to be working on. But even in its current state, we've already seen it help a lot, and we feel at this point it can help others as well. So we are still going to actively continue to work on it and improvement, but now we're going to be doing it in the open. We've even made it really easy to get started. Created an example app that only takes a few commands. You can get started running with sample data, see how it works on your laptop. I wrote a React wrapper and a web component wrapper around it so that if you use either of those technologies, it'll integrate simple. Yeah, special thanks to 2 people on my team. Jeremy Tatelman, he's our senior UX designer for our org. He's been instrumental in getting it to where it is today, as far as the UI and the intuitive aspect of it. And Luke Kasevsky, he helped build the prototype backend for the data while I could hack on the front end. So yeah, it wouldn't be where it is without either of them. And that's all I have. If you have any questions, come find me after, and I have stickers if anybody wants any.
Hello all, my name is Brian Brazel. So I thought I'd tell you who I am first because I've got you for the next 30 minutes. So I am an engineer who cares about production. I'm one of the Prometheus core developers along with Julius, Fabian and Bjorn. I run Robust Perception, the world's only company providing consulting and support around Prometheus. Previously, I worked at Google for 7 years and did a fair bit of monitoring, not as my primary job, but in order for me to be effective, I need good monitoring and good metrics in order to figure out where to look at with my logs, my profiling, and my code searches. And I've also been doing open source stuff for probably 15 years. So, I get lots of questions talking to all of you about what Prometheus is. At its core, Prometheus is a time series database. And we use it for white box monitoring. That's looking inside your application from information your application is collecting. And we make trade-offs for operational monitoring. It has two things that make it really powerful. The first is it has labels, which some systems call labels, dimensions or tags. So those are key value pairs associated with everything. It also has an extremely powerful query language, which lets you take advantage of those key value pairs, slicing and dicing any way you want, and graphing and alerting both use the same language. So if you can graph it, you can alert on it. So to look at some of the history, Prometheus is inspired by Google's Borgmon monitoring system, which I think was talked about last year on this very stage. It was started in 2012 by some ex-Googlers working in SoundCloud. To be clear, I never worked in SoundCloud, because that's a common confusion. It's primarily written in Go, which was a good choice. We publicly launched about a year and a half ago, and we're just prepping to launch our 1.0 as well in the next few weeks. It's independent of any one company, and we're currently incubating with the Cloud Native Computing Foundation to give us long-term governance. It's a very, very healthy open source project. As of January, it had 250 people contributing. So that means we've got an extra, 20 contributors a month. And even just this morning, as I was, fretting for this talk, I noticed, hey, someone filed the bug report. And 40 minutes later, by the way, here's the pull request to fix it, which is awesome. That's awesome you want. There's also a whole pile of third-party integrations. And to give you an idea of how easy those are to write, most of them were created without the core team ever knowing about it. And there's also hundreds of companies using it. It's always hard to estimate how many people are using an open source project because it's an open source project. But I do know that I think 5 sponsors of this conference are using Prometheus, as far as I know. So I want to kind of look a bit at the architecture of Prometheus to give you an idea of how it works. So Prometheus is a pull-based system. No booing, that's a good sign. So the problem with pull is, okay, how do you find everything? Which is a valid question. Because with push, it kind of just works, right? You just need to find what to push to. So what we have is service discovery. We will go out, we'll talk to EC2, we'll talk to Azure. GCE, someone sent the pull request on Monday, we're still reviewing that one. We can talk to Marathon, we can talk to Kubernetes. We've got 2 different ways of pulling data from Zookeeper. We can talk to Console, get that information, and figure out where all your machines, where all your applications are. And if you don't have those, we'll do JSON as well. And then we might say, hey, we've got some C advisors. If you've got Docker instances, which you probably do, C advisor will give you all the C group stats. It directly exports Prometheus metrics, so great, we just go and grab them. Perfect. Cassandra, something a little different. Cassandra does not expose Prometheus metrics. Someone's actually working on that. Anyway, but it does support JMX. So we use a JMX exporter to get all those, pull out all those nice labels. We go scrape that. You might also have some batch jobs. Now, batch jobs have a little problem with pull, because it's kind of difficult to pull from a job that no longer exists. We don't have time travel. So what we do there is we've got a binary called the push gateway. So at the end of the job, it'll say, hey, I'm done. I succeeded. I took this long, processed this many records. It'll cache the last run. Prometheus goes scrapes it. So all this data is coming in from all these systems, different systems. Some of them support Prometheus directly. Otherwise, other places we've got exporters to deal with it. And that's all coming in, all being buffered, all being written out to SSD on the local machine. Then we apply the rules and the alerts. These are Prometheus expressions. Some systems call these standing rules or persistent queries. And alerts are just a form of those that happen to send on to the alert manager. So all these Prometheus servers are sending to the alert manager. It then talks to PagerDuty, Slack, HipChat, email, and we can chuck JSON into the void if you want to as well. Then the final part is how do you get data out, because I like pretty pictures. The answer is we have a HTTP JSON API, and Grafana is what we recommend. All the dashboarding solutions out there, you can write your own. They all use the exact same HTTP API, which is all nice and public. So that's roughly how Prometheus works. Because the thing is as well, we're kind of looking at things that already exist. And it's nice to monitor your existing infrastructure. But we kind of want to monitor your applications as well and your business logic. If you think of your microservice architecture, right? It's kind of a tree, hopefully acyclic, right? And for each of those components, you're going to monitor your request rate, your errors, and your latency, right? Those are the three basic stats for an online serving system. But if you look at one of those microservices, internally, it's going to have a fractal state. It's going to have some libraries, some subsystems that are also talking to each other in a tree, which is hopefully acyclic. And you should monitor those in the same way. And the principle of Prometheus is that each of these libraries is instrumented, and then Prometheus kind of comes and grabs that on a regular basis and gives you those level of insights into your application. And to do that, we have client libraries, just like most other things. Ours are a little different in that our client libraries aren't just about marshalling data, because we have our own custom data format. They also take care of all the bookkeeping. They care of the current currency, and we try to make it as easy as possible for you to use them. So this here is a complete example. First off, you can install it via pip. So this is a Python example. Then we can create a metric. Here, request duration seconds. It's a summary. And there's a help string as well to help you remember what it was. Because when you start having thousands of these, you will forget. And you can call it directly, request duration.observe, 7, it took 7 seconds. Or you can use a decorator here in Python to just say, hey, this function automatically take care of it for me. And that takes care of exceptions and all the nitty-gritty for you, making it as easy as possible for you to use. You put your code here. Obviously, this isn't going to do much because that's saying do nothing, and a HTTP server. Now, some of you are looking at this now and saying, wait a second, seconds? Are you telling me Prometheus can only handle seconds? The answer is no. Prometheus has full 64-bit floats. And so it means we can use seconds here. Because some systems only do integers, which means that you, as the person instrumenting the code, has to choose the unit. Do you choose seconds? Do you choose milliseconds, nanoseconds, microseconds, picoseconds? And sometimes you're just trying to control what's going to end up on the other end in your Grafana and your dashboards. And I say that's silly. If you're instrumenting, you shouldn't care what the unit is. In the same way that you wouldn't store a time zone into a database. You store Unix time, right? And leave the time zone to the presentation layer, your dashboard layer. It's the same with Prometheus. Hey, let's use base units like seconds because we're using floats. It works. The other thing is, wait a second, that's a 64-bit float. That is less precision than a 64-bit integer. Isn't that going to be a problem? So a 64-bit integer has 53-bit mantissa. That's the precision part. 53 bits, it turns out, let's say you had some metric, which you were incrementing 1,000,000 times a second, which is pretty fast. How long? Well, there's reasons why you use that. No, it's 1,000,000 times. That's going to cover you pretty nicely. How long until it overflows? So you can do the math, and it works out as 274 years. So we do have to advise everyone, please restart your servers at least once a century. The other thing, as well, is that, if you're writing some application code, it's kind of annoying that someone says, oh, use this instrumentation, that library, that one, oh, I've got this monitoring system. Prometheus is an open ecosystem, okay? We take open source seriously. So yeah, you can go and expose over HTTP and it all works nicely with Prometheus. But it's also 2 lines of code to push out the graphite, because that API is there, and I think that's only 20 lines of code in the back end. So if you want to push out to any other monitoring system you already have, you can do that. That means that you as a library author or as an application developer who's giving code to other people can say, look, we've instrumented with Prometheus, you can use it whatever you want, just add 2-3 lines of code. And that's pretty neat. In fact, in Java, it's fewer lines of code to export to Graphite than it is to Prometheus. Yeah, because I can control the Graphite API because I'm writing it, whereas servlets. The other thing is, though, that goes the other way. Because Prometheus clients can also parse the Prometheus data format. And we've got a whole pile of exporters which can take data in, whether it be InfluxDB, CollectD, StatsD, CloudWatch, JMX, SNMP, there's a few others, Graphite, and produce it into Prometheus data format, which gives us some interesting options. So sure, you could have Prometheus going great to C-Advisor. But maybe you want to send C-Advisor to Graphite, which it kind of already supports. You could have a little bit of Python in the middle. Or another example, there is a monitoring system called Zmon, which is produced by Zalando, which is a German clothing company. Think of it as a distributed Python Nagios. And they actually do this. They run the node exporter, which is Prometheus's machine agent. They're not running Prometheus in this part of their system, but it's going scraping the node exporter, grabbing some stats, and doing checks based on that. So they've been able to take advantage of the fact that we figured out how to parse /proc and being able to reuse our work. And that's awesome. Let's do more of this thing. Another example you might have is, let's say someone's written an application that only exports to InfluxDB. The good news is InfluxDB's data model is pretty similar to Prometheus's. So you can run an InfluxDB exporter. You could have a little bit of Python going scraping that and push it out to, say, hosted Graphite. So you can use Prometheus as a clearinghouse to take care of all your metrics, and hopefully we can kind of start standardizing. Because it frustrates me as a monitoring system author that every single one of us has to reinvent the wheel. Every one of us has to figure out, how do I get data from Cassandra, from MySQL, from Postgres, from everything. This is silly. Let's see if we can just reuse each other's work. That'd be kind of nice. Of course, labels are where things are really nice. Because if you're used to Graphite, you're used to dotted strings. Metric, Monitorama, Portland. And that's great, until someone puts a dot in there and all your globs break. Escaping, people, escaping. But Prometheus, it's all key value pairs, and those are unordered. So we can cut and slice whatever we want. In fact, the values are full UTF-8. We have seen the Unicode Snowman, someone did it. But then you can slice, dice, aggregate any way you want. So here's an example of some of the power. Let's say you've got a whole pile of Docker images, like your company's really gone all in on that, and you'd like to save some CPU. So you want to know, across my entire fleet, what Docker images are using the most CPU, so you can know where to focus your efforts. So here's an example of how to do that. So here we've got container CPU usage seconds total, which is one of the metrics C-Advisor puts out. We use rate on that to basically say, hey, what's the per second value? Add them up by Docker image, so we're ignoring all other factors. We're ignoring the environment, the data center, the instance, the machine, everything else. Add them all up and give me the top 5. So now you know where to focus that optimization effort. And that's kind of nice. That's just a small taste of the sort of analytics you can do in analysis. It's also really good for alerting. Let's say that you want to alert when machines being down. Now, one of the little things about pull, people ask, hey, how do we tell when something's not turned on? Do we like ping it or something? The answer in Prometheus is we have a time series called up. If a scrape succeed, it's 1. If a scrape fails, it's 0. Pretty simple. So all we need to do to test an instance being down is go, hey, if up is 0, alert. And the thing is, if you look at this alert, it's saying up with a job equals node, we're looking at the node exporter, but it's got no other labels. So that means as service discovery discovers new instances, this alert automatically works for them. There is no effort, no code changes required. As instances appear and disappear, this alert automatically works. But we can be smarter than this, because we shouldn't care about a single machine being down, right? Maybe we care about, well, all hell's broken loose, and a quarter of machines have broken down. At which point you probably have a busy pager. We can take the average of all those 1s and 0s and say, hey, if it's less than 0.75, that means, that a quarter of our machines are down, and we get one single alert about something that's definitely a problem, and go look at that. And you can combine these and composite these any way you like. Because Prometheus is not just about monitoring machines. Prometheus actually has no notion of a machine. All it has is key value pairs with the labels. Because you should be looking at services. You don't care if one machine is slow, as long as the experience you're providing to your user is in line with your SLAs. And you can do that with aggregation. Prometheus as well, because once people start using labels, they don't stop. So you kind of need to be really efficient. So let me give you an idea of just how efficient Prometheus is, because Bjorn, who's done a lot of work here, there's talks at GopherCon and so on, which are awesome, you should go check them out, has gotten it to the point where a single Prometheus server can handle 800,000 samples per second. And this is Prometheus, so we're doing lots of in-memory stuff in the clients. So that's not 800,000 events, that's 800,000 samples. To put that in perspective, the node exporter, our machine agent, produces 700-ish time series because we troll /proc. The exact number depends on how many CPUs, network cards, file systems, and disks you have. But let's say 700-ish is a kind of a typical number for a moderate machine. And let's say you were scraping that once every 10 seconds. A single Prometheus server is capable of handling all those metrics for 11, 12,000 machines, which is kind of impressive. And considering that you'd normally run one Prometheus per data center just to keep your failure domains not mixed up, that means you only need one Prometheus, which means you don't really have to worry about scaling because it can deal with it. The other thing as well is that we have our new var rate encoding, which is based on Facebook's Gorilla paper, which is pretty awesome. And we've gotten it down in production to 1.3 bytes per sample. Facebook reported 1.4 bytes per sample, so it might just be noise and different data, but we're pretty pleased with that. It's also Bjorn's work. Prometheus is also decentralized because pull-based has one advantage of pull is that, well, if I want to test something out on a push-based system, I'd need to go and reconfigure the entire fleet to also push over to my new system where I'm playing around. With a pull-based system, well, I just start up Prometheus on my workstation and play around. It works. Which also means you're a bit safer against rogue systems. I think we've all done it, where we accidentally interfered with production because we were testing something on our workstation. Yeah, we've done it. So it pulls a little safer from that standpoint. But we can take this a step further. We can't just run a Prometheus on our workstation just for testing. What happens if we give each team their own Prometheus? Rather than having to go to a central operations team and say, you know, would you mind hooking these up, please? Each team controls their destiny, is empowered to do what they want. So if you're doing DevOps, whatever that is, then each of your microservice teams, you know, once you've completed all the buzzwords, can go and do what they want with their Prometheus, whatever makes sense for them. So let's take an example. You have a node exporter, you've got some machine somewhere in EC2, and we're grabbing a whole pile of metadata from EC2. The infrastructure team, they're thinking EU West 1, and this is availability zone A. This is the way we think of the world. Now normally, in a company, you've got one central monitoring system. The infrastructure team wins. They decide what the taxonomy is. But with Prometheus, it's not that way. Whoever runs the Prometheus decides the taxonomy. So some other team was like, I have no idea what EU West 1 is. But I know what Ireland is, because that's where EU West 1 is, and this is our production environment. And they're scraping the exact same node the same way. Maybe someone else is doing horizontal monitoring. They want to look across the entire fleet and look at some weird network stats. It turns out Linux puts out about 200 weird network stats, which you can normally get via netstat-s. And they just want to look across the entire fleet. They don't care about any of these notions or whatnot because they're trying to track down a kernel bug. And you could use the same idea for any application level things, looking across the fleet for a library in order to make business decisions and engineering decisions. So you have this power where you can empower everyone and choose the taxonomy that makes sense for each team. Prometheus is also reliable. Now, on one hand, you don't need your monitoring system to be more reliable than what you're monitoring. If you're monitoring a system that only needs 2 nines of reliability, a 6 nines reliable monitoring system is probably more work than it's worked. But you also want a monitoring system that works when your network's falling apart in an emergency. You want something you can rely on as your first port of call. And that's what we want Prometheus to be. Prometheus has no external dependencies at all. It needs local disk, preferably SSD, and it needs to be able to talk to whatever it's trying to get to. And that's it. And this is interesting because there's lots of systems out there that depend on Kafka, Zookeeper, Cassandra, Hadoop. And that's all well and good until the shit hits the fan. And all those CP systems that are doing consensus fall apart. Whereas Prometheus, well, it's a single server. It just keeps on going because it's not trying to do these very difficult distributed systems problems. And for high availability, we also keep it simple. Our way of doing high availability for Prometheus is you run 2 identical Prometheus servers, both doing duplicate scraping, both sending alerts. And our alert manager will take in those alerts and deduplicate them. Nice, simple, obviously reliable, because there's no complex clustering in there that takes years to get right. And we can go a step further. Because everything's going through a central alert manager system, we can group alerts. So maybe you don't want to get one notification for every single machine. Maybe you say, no, aggregate them by data center. So you receive one notification about every machine that's having a particular problem. Or maybe you want to go the other direction. Maybe you've got a propagation delay alert, which, is caused by the root. So it's happening across all your clusters. So you decide to aggregate that one by alert name. Once again, you're now getting one notification instead of one per data center. And this is getting closer to the ideal of one notification per incident, because you want to keep your signal-to-noise ratio good. And we are as well working on making the alert manager HA, Fabian's working on that, and we're using eventual consistency for that to make sure it stays reliable and simple, because eventual consistency is easier to get right than consensus. As a project as well, we are opinionated, and not just about pull. We try to avoid reinventing the wheel, because we know we are limited in our time. There are many, many yaks we could shave, and we've decided not to shave. So one example we have is PromDash, which is a Ruby on Rails dashboarding system. It's very similar to Grafana. And maybe about 9 months ago, someone added a plugin to Grafana, which ultimately ended up being a first-class support for Grafana for Prometheus. And we went, you know what? We have to keep maintaining PromDash. Or we could use Grafana. Let's use Grafana. So PromDash is now deprecated, and we recommend everyone to go use Grafana, which I'm sure you can learn about more in the next talk. And there's a few other places like that where you've said, we're going to avoid scope creep. We're just going to try and focus on what we do really, really well. We also try and encourage best practices. Okay? If someone comes to us and say, can you do X with Prometheus? And we'll go, you should use this solution instead. So one example we've seen a few times in the last few weeks is someone wants Prometheus to restart their servers automatically when they die. Okay, so you'd have a node exporter going to Prometheus, going to Alert Manager, sending a parameterized JSON request to a script executor, which will restart your process. And that'll all work, that's all supported. I implemented some of that stuff myself. Great. Or you could use a supervisor. Use systemd, use daemon tools or whatnot. Use Monarch. So we'll kind of try to point you in the right direction because we want people to use the best tool for the job. If it's not Prometheus, we'll tell you that. So we have the live demo now. Let's hope it works. Pray to the demo gods. So this is on demo.robustperception.io. So here's an example of actual Prometheus metrics. So you can see here, the labels is just brackets. This is our text format. And here, for example, is the CPU stats. So you can see it's broken out by CPU and mode. This is only a one-core box, so it's not very interesting. But you notice these numbers seem to be a little on the big side, because Prometheus uses counters, which kind of go like that. Up and to the right is good, but I don't want to be trying to figure out the angle that's going at, because that's the total CPU used since the process started. So what we can do is use the rate function to convert that back, stack it, and hey, I can see this CPU system is using about half its CPU. So that's a very, very simple expression with Prometheus. And we've got Grafana as well. There we go. Full integration there. And you can take advantage of labels and Grafana templating to automatically pick up all your machines. So that host name is not hard-coded anywhere inside our Grafana configs. It's been picked up dynamically. Of course, it's not very interesting because this Prometheus is just monitoring itself and the rest of the machine. Here's the alert manager. I've got just a sample alert here, but you can also silence alerts. So if you know what maintenance is coming up, put in a silence based on labels again. So you say this entire data center, no alerts for the next 2 hours. Because once again, you don't want to be paged unless there's an actual problem. I'd also like to show you a little something I'm proud of. I may horrify you, and let's hope we've got internet. Yes. Using the latest in web technology, HTTP meta refresh. So this depends on the Wi-Fi. Now, for those of you who have, oh, is that lighter? Is it? No, it is not. I've been waiting to see it lighter. For those of you who haven't studied computer science, Conway's life has been demonstrated to be Turing complete many years ago. You can build a Turing machine in it. That means if it's possible to compute it, it's possible to compute it with Conway's life. And because I've implemented Conway's life in Prometheus using the query language, that means that PromQL, our language, is Turing complete. Yeah. Which means it's just as powerful as Ruby or Java or Go or even Haskell, Don't do this in production. Please don't do this in production. But it's just an example of just the sort of thing you can think about doing. And in case you're wondering, yes, here's the expressions for that. This is likely the most complicated thing that has ever been written in Prometheus, and hopefully it'll stay that way. The one thing we aren't good at doing is random number generators, which is why we're just using time, and it mostly works. Cool. Okay. Cool. Oh, come on, yeah. There we go. So just to kind of summarize, what defines Prometheus? Prometheus is open source. We're an open ecosystem. We want to help everyone. We make our instrumentation easy, and you can use your instrumentation without using the rest of Prometheus. You can benefit from it. It's powerful due to the labels, due to the query languages take advantage of those labels. It is extremely efficient because one machine can plausibly monitor 12,000. It is decentralized, empowering each team to do what they want and not having to talk to a central ops team to manage their monitoring. It's designed for reliability, so it can be the first thing you go to in an emergency. And it is opinionated because we want to do one thing and we want to do it very well. And we want to help you succeed. So here are some resources. The main website is prometheus.io. We've got a Google Groups list. We mostly hang out in IRC on Freenode, #Prometheus. The demo I just showed you is demo robust perception.io. My blog's there. Once a week, some blog on Prometheus. If you're using Prometheus, you should be doing that. And queries there. So are there any questions in however much time I have left? Oh, 5 minutes for questions. Any questions? Let's see a hand. Yeah, up there.
How would one go about trying to transition from a graphite-based monitoring push to Prometheus full?
Okay. Okay, so the question is, how would you transition from a graphite-based push to a Prometheus-based pull? So as a first order step, just to try things out, because you want to try things out before fully committing, no, it's just good engineering practice. It might be awesome, but still, that doesn't mean you can throw caution to the winds. We have a binary called the graphite exporter, which can take in graphite stuff, only the text format, not the pickle one, and convert it into Prometheus metrics. So that's good for getting you started. Ultimately, what you want to do is instrument all your binaries with our client libraries. But even then, like a good place in general to start is the node exporter, or the MySQL exporter, or the JMX exporter for Cassandra. You take existing infrastructure and you monitor that. Because to be honest, going and saying all to your developers, hey, we want to change it to this new instrumentation library, that's a hard sell. It's saying like, yep, we're going to spend the next 2 months converting over to Prometheus instrumentation libraries. Start off simple. Start off with something like the node exporter. We probably give more metrics than every other system in terms of machines because we're basically just trawling all of /proc and /sys and work from there. And over time, get your infrastructure. And then once everyone's used to it, everyone's happy, everyone's committed, then we can start talking about the big stuff and going directly to direct instrumentation and ultimately getting rid of the graphite exporter inside your setup. But we do have things like that for transition, for CollectD, for StatsD, for Graphite, for InfluxDB, all of those we have them. Cool. Yeah, question there?
Have you guys given any thought to sort of a cookbook for the PromQL?
So the question is, has any thought been given to a cookbook for PromQL? Yes, we're also very busy. So like one of the things like I'm sure Torkel mentioned Grafana.net, so there'll be dashboards there and we'll get around adding stuff there. There are some examples, like you can crib some stuff we're doing. The big problem with monitoring, it turns out, isn't so much writing the expressions, because there's only like 5 or 6 common patterns. It's actually knowing what metrics to plug in there. And figuring out the expressions is pretty easy. So when and you get a dashboard from somewhere, the real thing is, someone's figured out the important metrics. Not, someone has figured out the expression, because there's very few expressions which are particularly complicated. Cool. Any other questions? Anyone?
Can you describe the time series storage?
Sure. The question is, can you describe the time series storage? So we have metadata sitting in LevelDB. And then the time series storage itself is custom, and it's 1 file per time series. Don't worry, you won't run out of inodes. We were initially using, I think it was LevelDB purely, and that didn't scale at all. But now it's basically a file per time series, which is one of the reasons we recommend SSD, and we're just batching out writes to that. Because most queries as well are kind of just want a chunk of time series, so that's efficient to get. And most stuff's going to be coming from memory anyway. So things are basically 1024 byte chunks in memory. I think that's 1050 or something with the header on disk. But there's an FAQ at some point. Jordan will write a paper about all that.
And is it round robin?
Okay. The question is it round robin? The answer is no. Prometheus stores the raw data with no downsampling. Because, well, A, it's very efficient, and B, we believe that downsampling is the job of long-term storage. Any other questions? Oh, there's a question.
Do you support anything besides strings or label values?
So say that again, please.
Do you support anything besides scalar strings for label values?
Okay.
Collections, for instance.
Okay, the question is, do we support anything other than scalar strings for label values? The answer is no, we support strings. But if you wanted to do like an array, what you normally want to do is have multiple time series with different values for that label. Which I hope answers your question. Okay.
One question.
Which time? Okay, we've got one last question. Yep.
One question. So you were saying that you expect, you want to give one Prometheus server per team.
Mm-hmm.
One of the challenges is if people really cared about their service being up, you could like do that, but most of the time, people, like you need external monitoring because people really don't care if their service is being up. So I was just wondering, in this model, like does giving each team its own server is a good idea in practice?
Okay, so the question is, people might not care about their systems being up, and my suggestion then of giving one Prometheus per team, is that a good idea? The thing here is that you're asking the wrong question there. If your teams don't care about their monitoring individually, you have bigger problems. Because, to be honest, just one Prometheus per team is just one suggested deployment model, because it normally ends up that way organizationally anyway. You could run your Prometheuses for them and have them centrally as well, like that's a good way to start out. But this is really more a social question, which I think was covered a lot in the first day. You can do it whatever way you want, it's just a suggestion. And I think that is it. Yep, good, thank you.
For BMC.
Hi everybody, I'm Michael Moran. I'm an architect at TrueSight Pulse at BMC. And I said those words and you probably thought to yourself, who is BMC? Somebody may have a couple ideas what you think it might be. Maybe mainframes, potentially punch cards, dinosaurs, and that's somewhat true. And that's fine. We have a lot of mainframe customers we love a lot. So your next question you're thinking is, so why are you here? Why are you guys at Monitorama, and what do you want from me? So about a year ago, BMC bought a company called Boundary, who some of you may remember. We've been working together for the last year to launch a product called TrueSight Pulse, which you can see up here for 1 sec. Get a demo going. That's a little harder to see. See if we can shrink that a little. That's going to be tough. All right, well, that makes the demo a little harder, doesn't it? All right, what we can see up here is way too many graphs for the resolution that we have, but we got a bunch of things that are going. The first is you can see, make that a little bigger. You can see there's an agent that's running that's pulling all of your system stats. The agent's written in C, so it's super lightweight, no dependencies. Really, if your monitoring is taking up more CPU and more memory than your actual application, you're probably going to have a bad time. So we've tried to make that as easy as possible. The second part is a very rich plugin ecosystem. We write all of our plugins with the intent to write them in Lua first. There's a Lua interpreter built into the meter itself. That way we can have, again, no dependencies, so you don't have to install any special software. Click a button in the UI, plugin comes down, you can see it, little console log through, or you can roll them out through Chef, Puppet, Ansible, Salt, whatever your stack is of choice. So if you're trying to do it just in the UI to play around or at scale, it supports both of those ways. There's also some pieces in there for how do I actually get my data in. So if you're using StatsD, there's a StatsD server built in there, so you can send all your data locally to the agent. We'll collapse all the data and send it up. The big part of that is we support multiple versions of StatsD, so if you're using the CollectD implementation or the Etsy implementation, there's some slight differences you can tweak with the config file, so that supports nice and easily up there. There's alerting that's based on your intervals and on your aggregates to make sure there's a little less noise so you don't get woke up at night. We also use DropWizard and Java a lot, so we've written our own syncs. That's been open sourced and is now up on our GitHub, so you can just add that into your app. All your metrics will flow. There's also a socket that's built in so you can push in your metrics locally too. So if you want to write your own, you can do that. If you want a client library, we have that. And if you're using DropWizard and want to sync, we have that. So that's all been open sourced and sitting up in the GitHub right now. And that's all 1 second data that you see coming through. You might ask yourself, why do I care about 1 second data? And for those in the audience right now who've had problems where that 1 second data would have helped, 1 second matters when you actually want or need 1 second. So for those who have had that problem and needed that 1 second data, that's there for you. The best analogy I've heard so far is I met my doctor and I say I have a problem with my heart. I have an arrhythmia and he's trying to figure out what's wrong with it. So he hooks me up to an EKG machine. First beep goes off, beep. Beep. You're gonna have a really hard time diagnosing what's wrong with you. So the same way you protect your body, the same way you protect your heart, their servers are the lifeblood for your applications, so protect them the same way. There's a free trial if you want to sign up at truesitepulse.bmc.com. If you have any questions, you can see us out back after. Have a great night.
And
Welcome to Grafana Masterclass. So this is presented as part of Monitorama summer course series. And lesson 1, who am I? So my name is Torkel Ödegaard. And I look like this. At least after 2 years working on open source from home. You kind of end up looking like this. It also sort of shows some symptoms of sort of Stockholm hipster syndrome. So, which you end up sort of with a outgrowth on your head in the form of a hat in the sort of later stages. I'm not sure, are there any hipsters here in Portland? I love this saying, I'm not sure if you heard it, Portland is where young people go to retire. Makes me want to move to Portland and retire, maybe open a brewery. The city could need one more. Lesson 2, what is Grafana? So, if you don't know, Grafana is an open source project. It's a dashboard tool for visualizing time series. You build these dashboards composed of different types of panels, mainly a graph panel, or that's sort of a very feature-rich panel. It's about 2 years old, very easy to start using, and it's all about time series visualizations. And I created it sort of originally for application monitoring, and the main use cases for people here, I guess, and the main use cases people use Grafana for is infrastructure monitoring and application metrics. But yeah, still that's only about 60% of the Grafana users, because it's used in so many other sectors as well, as sort of home automation, Internet of Things. Just a couple of weeks ago, I talked to an agricultural researcher who put sensors in the soil to visualize sort of soil health using Grafana, which is kind of cool. It originally started just supporting graphite, but sort of over time, more and more sort of data sources has been added through a plugin system, and this is just sort of a couple of them. There are many more. But just let's sort of back up a bit and just want to tell you how special Monitorama is for me. Because I was here 2 years ago presenting at a stage where Grafana was only about 4 months old. And it had, during that time, very quickly gained a sort of very sort of passionate and users that really loved Grafana. And even though there existed a number of alternative dashboards for graphite, Grafana just took off. And Jason invited me to talk here, and the love and feedback and sort of encouragement that I received 2 years ago was just so amazing, and it really solidified my sort of plan to work on Grafana full time and sort of quit my job and do that, which I did, and I now sort of worked on Grafana full time for 2 years. And in that time, we have sort of done a couple of major releases for Grafana. We had a tremendous sort of growth in the project, in the number of really cool users we have. Just amazing sort of the level, the scope, and the coolness of all the companies that are using Grafana. And especially last December, when the first time the SpaceX launched and landed their Falcon 9 rocket, in their promotional video, you could sort of spot Grafana being used, which was just sort of blew my mind a little bit, that sort of one of the most sort of inspirational companies around is using Grafana. And that kind of also inspired us, or inspired the design for our latest poster. So yeah, which is pretty amazing. So yeah, I've been working full time on open source, which kind of reminds me of this comic strip. So how do you think open source apps are maintained? And how they are really maintained? Just one more ticket. So when you work on open source, it can be really addictive and obsessive. But luckily, I met a couple of awesome guys in New York 1.5 years ago, and we decided to start this company, Raintank, and Raintank has really sort of done so much work for Grafana in allowing me to work full time, allowing me to sort of hire some great people in Stockholm. And while it might not be like this, it's more like this. You have lots of hangouts and talk with other people that way. And lately we had an awesome addition to our sort of daily stand-ups and weekly meetings in the form of, Hugh Laurie, or Jason Dixon. It's going to be awesome to get the chance to work with you. Enough slides. That's not why I'm here. I want to demo and show off some cool Grafana dashboards. So let's start. That looks better. The resolution on this projector isn't the best, so it might be tricky to read some of the text. But if you're not familiar with Grafana, you build these dashboards composed of rows, and in these rows you add panels. So if I add a new graph panel to this row, it will sort of enter full screen edit mode, and I'll get thrown into the metrics tab. So let's just pick a graph here. You get thrown into the metrics tab, and the metrics tab right now looks the way it looks because this is using a graphite data source. And here I have the metric key and a bunch of transformations that are being done on this metric request. But if I change the data source to something like Elasticsearch, I get a completely different sort of query editor that exposes all the query features in Elasticsearch. And there's a sort of dashboard picker. This is just sort of, if you're not familiar with Grafana, you can also add a bunch of sort of data sources in the data sources sort of admin view. A couple of things that I kind of wanted to highlight in this dashboard as well is snapshotting. And if you sort of have zoomed into a specific issue that you can maybe want to sort of store exactly this view for posterity or share it with an external client, you can use a feature called snapshots. And snapshots will just sort of store everything that you see, all the metrics in all the panels, and sort of embed that into a separate copy of the dashboard that includes that data, which will sort of look the same for eternity. And it's also something that you can then sort of publish to an external Grafana site or something that you can then share with another user. And these snapshots are also sort of something you can sort of then go back to a couple of weeks or a year from now, and the data will look the same. So that's a kind of a neat feature that many don't know about. Another feature that might sort of not be super apparent is the feature that Grafana can actually render all the panels to a PNG image. If this works, that is. I usually develop on a so not on a Mac, on a Linux. So it's I blame Mac. This is all running sort of in Docker. Okay, so you get an image. It's super useful for if you sort of want to have automation around Grafana that sort of builds reports into PDFs. If you have a Hubot or chat integration, you can sort of then render these any panel to a PNG and share on Slack. Now, I have a lot of dashboards to show. So if I'm going to go go through these quite quickly, because I'm sure you have lots of questions as well. And also, I just want to highlight a few features that are core to Grafana, but also maybe are not super intuitive or super you might not be aware of them. Another sort of small thing is that Grafana can do logarithmic scales. This was something that, to me, I just didn't know what the use case was, because from a developer's perspective, it's a logarithmic scale sounds like something that sort of data scientists, or if you have very sort of exponential curves, that you might want to use logarithmic scales. But it is actually super useful for latency data, where you have sort of extremely high variation or orders of magnitude differences, and also in sort of data storage and memory. And the scales you can just select both for left and y-axis. So let's see, back to the home dashboard. So on that fact, you can actually now in Grafana, in the latest Grafana release, you can actually modify, in 3.0 you can actually modify which dashboard is your home dashboard. So in this case, I've actually specified Monitorama as my home dashboard. And this is something you can do either on the user profile set your home dashboard and UI theme. And this is also something you can do as a sort of set defaults on the organization level. So back to more demos. This is just a minor feature that could be useful if you have sort of a min-max, an average, and you can sort of visualize that using a feature called fill below to. And this is also sort of, the reason I talk about this is that in the display options, you can actually have specific display options for a specific series. So in this case, I'm saying sort of that the max series shouldn't draw any lines, and you should fill below to the min series. And then I sort of disable lines on the min series as well. And these sort of series-specific options allow you to do sort of, I can say I want to have points as well for the max series, and just that series will gonna sort of be rendered using points. So yeah, you can create exactly the kind of graph you want to do. So that's why I showcase that feature. Let's move back to the start. Time range override. So this is also sort of a feature that you might not sort of use or be aware of, but you can actually override on per panel basis what time range that panel is going to use. So this panel down here is actually using the dashboard time range. So if I change to last 3 hours or something, this panel is going to change. But the other, when I zoom in, all the panels match that time range. But if I just specify last hour there, this panel is using last hour, but the other panels are using a specific time range for that panel. Last 10 minutes, last 6 hours. And this is all something that you specify in a time range tab. You can sort of specify either a time shift or a relative time or both. And another thing that I want to show in this dashboard is some effects that query aggregation can have. So in this single stat panel, we have we show we want to show the total of sort of payments done in the last 6 hours. But you might notice so that the total is quite isn't that much higher than the total for payments in the last 10 minutes. So something looks wrong. And one of the reasons here is that we're only requesting 100 data points from Graphite in this case. But it could be true for, the same issue is going to arise for other data sources as well. We're only requesting 100 data points, and that's just for, because we want to get the background graph. But we want to show the total as a single stat. So there's going to be some aggregation done by Graphite in this case, and that is kind of hidden in Graphite at least. It's more prevalent in the other time series databases where you explicitly have to maybe specify a query aggregation. But in Graphite, you have to add a consolidate by function to change the default consolidation function, which is average. So if I change this to sum, it will now sort of show a correct total. And this is more apparent if you use the legend and the legend values in Grafana. So in this graph, I'm showing you sort of min, max, and average, and total. And this is something that kind of makes me upset sometimes when I see screenshots of Grafana and you have sort of min and max and average at the same time in the legend. Because due to some limitations in almost no time series database supports returning average, min, and max for the time range per series. So Grafana is calculating the min and max and average and total. And that is done after the query is sort of going through downsampling and aggregation in the time series database. Because if you return raw data, this is looking at the last hour. So this is fine. If you look at last 5 minutes data, you're not going to have any data at all. But if you look at the last hour, that might not be that much aggregation. But if you look at like the last 7 days or something, there's going to be a ton of aggregation done in the time series database. And min and max cannot be accurate at the same time. So I just sort of want you to think about this, that if you have a legend you have to pick either min and max or average or total. They cannot be accurate at the same time. And you have to also sort of, if you want to have max in the legend, you might want to have also max as the aggregation function. Something to think about. Elasticsearch is actually the only one that I know of where you can actually do a group by time and get sort of min, max, and average for the whole time range as well in a single query. Okay, moving on. Templating. So this is sort of a core Grafana feature that is one of the sort of fundamental things that make dashboards more generic, so you don't have to create a dashboard per server, per application. You can just sort of create these variables. And these variables are something that, there are different types of variables. The main one is called a query variable, and all the values, options in this variable is sort of queried from the time series database. So if you add a new application, if you add a new metric, it will appear in this selection. So if you add a new application, it will show up here. If you spin up a new server, it will show up here. And these variables is then something that you can use in your metric query. You can use them in graph titles. You can use them almost everywhere. And that allows you to build very sort of reusable and generic dashboards. And another thing that you can do with if you have a variable is that you can also specify that this panel, instead of just sort of, I have two servers now selected, instead of just showing both in the same graph, you can say, okay, well, I'm going to split out this panel per each value in this server variable. And maybe I want sort of to have that at span 4. So if I select now all the backend servers, I get 4 panels instead. And if I also select the fake site, I get the panels for the web servers as well. So that's sort of super useful for creating more dynamic and reusable dashboards. Let's see, ignore. Another template variable is the interval variable. So if you go into templating, you can specify that instead of a query variable, this is just an interval, and you can specify different types of ranges, like 1 minute, 10 minutes. You can also have an order option that adapts to the time range. You just specify I want sort of 10, I want to split up the time range into 10 steps, something, no matter what the time range is. But this allows you to sort of change the granularity of the data you're looking at. So if you want to sort of look at the data in its raw form or it's in very sort of granular form, you can do that. And then very quickly sort of change. I want to look at sort of just day totals, and you can do that without sort of having to go into the panels and change a group by time or something. So let's see, moving on. This is a new feature that we released in 3.1, which I'm really excited about. It's was a top requested feature for a long time, and that's the ability to quickly change which data source a dashboard is targeting. So if you have multiple graphite clusters or multiple Prometheus servers, like that is usually the case, instead of just having to go into each panel and specify the data source, you can now create a data source variable where there's a new type called data source, and you just have to specify which type of data source this variable should be, and it will automatically fill in sort of all your data sources of that type. So if I add a new graphite server for a new environment, say, that's going to appear here. And for the panels, you just, instead of specifying a data source, you just specify that variable, and it works as you expect. So let's see. Moving on. This is just want to showcase how you can mix and match different types of data, and just also that sort of the thing I showed you about the template variables and templating and stuff, that works with any data source. So in this case, I'm using Elasticsearch, and this is a at this, a query variable that sort of will query Elasticsearch for what values exist for the host name field. So it's a terms query in Elasticsearch. So if you sort of write new log entries with new host names, that host name is going to appear here as well. And if I select sort of a couple of servers, this graph is going to change. And the templating system is very sort of smart in that this variable is used in this Lucene query, and when that variable is interpolated, it will sort of know, okay, I need to interpolate this in a Lucene context and generate a sort of a Lucene query for each variable selected, or each value. The thing that is interesting here is if you want to combine data from different types of data sources. So let's say I switch to a mixed data source. The mixed data source allows you to add queries of different data source types. So in this case, I have an Elasticsearch, and I maybe want to visualize the logs or something from Elasticsearch alongside CPU or login data from Graphite. And that's sort of something that is super easy to do with this mixed data source. You can just add a query from any data source, any number of them, and they will all be sort of rendered on the same graph, which is kind of neat. So let's see. Moving on. Annotations. Annotations is a way for you to sort of add log data and event data to your graphs. You can't sort of create new events like this from within Grafana. That's something we definitely want to do. So you can sort of maybe add a comment or mark a region and annotate that from within Grafana. But right now, you set up these annotations. Annotations can come from any source. It can come from Graphite, Elasticsearch, InfluxDB, Prometheus, OpenTSDB. And recently in 3.1, they become a little bit more powerful in that you can put more information in them. You can now actually hover over the actual annotation, and you can have links. And yeah, that sort of might direct you to an outage ticket or something. So that's pretty neat. Moving on. Grafana is not only about graphs. There are multiple sort of different panel types. This is the table panel, which allows you to visualize time series in a tabular format, but also allows you to sort of look at raw log data from Elasticsearch or other data sources that support that. There are different types of panels as well available on grafana.net. I'm going to showcase that a little bit later on. But the table panel is a core panel included in Grafana. And speaking of grafana.net, that's the next point on this slide, or next dashboard in this demo. And this is something that we very recently launched, the ability to share dashboards on, let's see if we have an internet, maybe not. Let's try to open one. Yes. Okay, so this is something we recently launched, and I'm super excited about this. And I will, almost for the first time, allow an open source community to collaborate and share their expertise in Carbon or in Cassandra or in MongoDB. This is the ultimate MongoDB dashboard showing all the core metrics. And you can sort of, instead of spending hours and hours of sort of figuring out what the core metrics are, you can just download a dashboard from here and be up and running in Grafana in sort of very short period of time. So just to show this off, I can sort of copy and paste this URL for this collectee dashboard, head back to Grafana and go into the import screen and just paste that URL. And this is the new part. So when you export a dashboard. It now includes a lot more information about which data sources were used, what type were they. You can also add sort of hidden variables that you can use as a metric prefix, which is super useful for graphite. So in this case, it's a collectee dashboard. I can sort of pick the graphite server I want to target, and I can, if I change to have a custom collectee prefix, I can specify that here. Save and open, and I have a sort of now a ready-made collectee dashboard for host metrics. And I added and super easy to publish on Grafana.net. I also did one for Memcached and Nginx. So if you think you have an awesome dashboard, please share it out on Grafana.net. So let's see. What more do we have? Dashboard sharing. It's alive. So what you're seeing here is a new feature in Grafana that allows a data source to push data to the panel, and not only sort of the panel to request data from the data source sort of API and the data source abstraction within Grafana. So this is just using a fake sort of data source to showcase the feature. The only real data source that is using this feature is the Snap app or Snap data source. Snap is the sort of collector agent from that Intel is working on, open source. It has an HTTP API that allows Grafana to connect to it and stream metrics directly to Grafana. And that data source is using this feature where the data source can sort of continuously push new data to the panel, which is something we will use more in the future. I think I have started working on, but not completed, a WebSocket data source for Grafana where you can sort of push live data to panels and graphs. So, plugins. Yeah, this was the main feature, or the most of the work in 3.0 went into sort of overhauling the plugin system and making it more feature-rich and robust and future-proof. And we also added new types of plugins. So we can now install very easily panel plugins and data sources and apps. And apps is like a collection of different plugins. So an app can contain other data source plugins, panels, and dashboards, and also custom pages. So you see, have this our world ping plugin installed. So can go to apps. You can see I have 4 apps installed. You can see there's an update available for the Sabix one. World ping is an app, and an app can have custom pages. And a custom page can have sub pages as well. And now I just want to navigate to one of the world ping dashboards. And if you attended our party yesterday, we had this sort of pool recording app that we just threw together in a couple of minutes to record all the trick shots and or how much you failed. It's super easy to build either a new panel or a data source and a whole app. Maybe the documentation can be better, but there's tons of examples out right now. So if I head back to Grafana.net, check out the plugin list there. It's just a ton of plugins, and all of them are open source. If you want to look at sort of how they were implemented, you can do that. So let's look at where I'm at. Okay, so and just one thing that I forgot to mention about plugins is that, I mean, we have also new in Grafana 3.0 is a CLI tool that makes it super easy to install plugins and update them. Just sort of Grafana CLI, plugins install, plugins update, plugins list. So that's interesting. Alerting. So this is something that is not going to be included in 3.1, but it's going to be merged to master after 3.1 is released. So it's something we've been working on for a very long time, and it's starting to come together. And you just need to mature a little bit more, but we're very close to merging it to master, and it's going to be included in the release we do in maybe late August or September. So the idea here is that you can sort of create, pick any query from within the metrics tab, and also then set thresholds. We're starting quite simple with sort of static thresholds, and just you can pick what kind of aggregation you want, and for sort of how long the time window should be for sort of evaluating this alert. We'll learn a lot sort of during the conference as well, get good ideas for how to extend the alert definition here to include sort of a markdown template where you can specify links to other dashboards and sections that should be included in every alert, like sort of what's the customer facing impact. And also maybe more history, sort of what's the previous values for thresholds? Have they been changed recently? That was also a really good idea. Anyway, we're making progress on alerting. So, one more thing. Here's a funny thing that we saw yesterday. Someone's added a new data source that they want to publish on Grafana.net, which allows you to, it's a sun and moon data source that allows you, that has a lot of data of the sun position and the moon position, which, yeah, sounds kind of interesting or strange. Why would you need that? But when you add this sun and moon data source, you specify your longitude and latitude position. This is the position for Portland. And with that, you can sort of get graphs for sun altitude, moon luminosity, and you can also get annotations for sunrise and sunsets. So this might seem kind of useless, but then you might not be a vampire or a werewolf, where this can be really helpful. So with that, I will turn to questions.
Just for log scale for time so that we can see trends in different durations.
Log scale for?
For time.
So,
Monthly, weekly, and daily on one panel.
okay. Yeah. Well, that's an interesting idea. I haven't seen that before. Is there any example? Sort of.
I guess another way to ask it is, what do you think is the best way to show trends at different time scales for a measure?
Okay. Well, I mean, the best thing I can think of now is have multiple panels with different time ranges on them. So, like the dashboard I had here, so showing logins last 10 minutes, last 6 hours, last day. You could do that sort of with day, month, week, year. So that's the thing I can think of right now.
How are alerts delivered to the recipients? What is it integrated with?
So we are, the idea we have right now is, so with the alert you specify notification groups, and a notification group, I mean, like it could be sort of ops or it could be, and you can have multiple of these, and the notification group can specify that we want warnings to Slack channel, we want errors to PagerDuty, and so a notification group can act as a relay and routing sort of system for multiple sort of goal endpoints. Any more questions? Yes.
So the storage of all the graph settings and stuff like that, what's the story for high availability of Grafana being something you actually have to have on the back end?
Yes, so I mean the high availability story for Grafana, I mean there's a backend written in Go, and you can cluster it. I mean you have to use MySQL or Postgres as the main database for the main database, and also for sessions if you want to, or you can use sticky sessions for the load balancer. For the alerting scheduler and execution sort of system, we plan to sort of have that sort of be aware through of the other Grafana servers and be able to split up workload and take over workload if you have sort of multiple Grafana in a cluster. Any other questions? Okay, well, thank you all.
Hey everyone, I am super happy to be here today. I'm going to be talking to you about how to teach an old monitoring system new tricks. No prizes for guessing which old monitoring system I might be talking about. My clicker's not working, that's sad. Hello, all right. We'll make it work. Hi, I'm Katherine Daniels. You can find me on the Twitters as BeerOps. I'm a senior web operations engineer at Etsy, co-author of Effective DevOps. So if you would prefer to stop doing DevOps ineffectively, check out the book. It's got a yak on the cover. And I am a frequent Monitorama attendee, unlike that Pete Cheslock fellow who has only been to 4 of the Monitoramas. This is actually my 5th one. So thank you to Jason for continuing to make this such an awesome conference and for continuing to let me come and say words. I am going to take you through a hypothetical day in the life of a web operations engineer at Etsy and kind of talk through some of the ways that we approach monitoring. So I'm going to talk about deploying new servers and deploying other changes to our old monitoring system. Going to try and explain some of the ways that we make getting alerts a little bit less annoying. Going to talk about sleep and on-call tracking, and I'm going to end with an on-call bedtime story. Etsy is an online global marketplace for handmade and vintage goods. We are also known as a monitoring and alerting company that also runs a website where you can buy handmade tea cozies. We've got our headquarters in Brooklyn, which is the office that I work out of. Some numbers, because everyone loves numbers and scale. We've got, as of the first quarter this year, 25 million active buyers, 1.6 million active sellers, and in 2015 we had $2.39 billion in GMS. That's gross merchandise sales, or the total dollar value of the tea cozies and other delightful goods bought and sold on our site. So I want to start out by saying that I'm not here to start any sort of flame war about which monitoring system is best. I know that there's probably people who are thinking, oh my God, why are you still using Nagios? You should be using some shiny new thing. And also you're pronouncing it wrong. It's Nagios or Nagios or... Let's not even go there. I'm not here to have that kind of argument with people. I'm here to talk about ways of customizing Nagios or maybe other monitoring solutions to suit some needs. Now, if you do want to have those kinds of arguments, which I'm sure some people do because we're people who have opinions about monitoring, shocking at a monitoring conference, my colleague Lori wrote a blog post explaining some of the reasons that he likes Nagios, why we are still using it, why it works for us at Etsy. He was really surprised to note that bit.ly/yay Nagios was not taken as a URL. So if you want to read some of his opinions and yell at him on the internet, feel free to go there and do that after this. It's also important to point out that even though Nagios is old and maybe not the best for some of today's new environments and infrastructures, it still is like the #1 most popularly, commonly used monitoring system. This was a survey done by James Turnbull, who literally wrote the book on monitoring. It's an awesome book, you should check it out. Nagios, #1. Also, there's 11 people who answered that they aren't using any monitoring tool, so if you're gonna yell at somebody, yell at those 11 people. Now, I will admit that Nagios is not the best fit for everything. There's all this new cloud, serverless, no-ops, whatever, that Pete stole my unicorn slide, but mine is pooping 100% uptime, so take that. I will admit that Nagios is not suited for every infrastructure in every situation, but if you do have, a more stable, a more static infrastructure, there are still use cases where Nagios fits. So I don't want to focus too much on the specific tool, but kind of how we are using it and how other people can use it. So I'm going to take you through this hypothetical day in the life of doing ops at Etsy. Unlike real-life ops at Etsy, this talk will have fewer cat pictures, but don't worry, there's still going to be cat pictures. So the first thing that you might do is build some new servers. Insert serverless joke here. Again, I know that it's the cool new thing, and some people like it and some people like me like to make fun of it because serverless is actually made of servers. There's still servers in there somewhere, no matter how much you abstract them away. And fun fact about Etsy, we actually love servers. We have 3 data centers, 2 in New Jersey, 1 on this coast for disaster recovery, about 3,000 servers overall, which means that we have to provision them, and then we have to get them into Nagios. Now, 5 or 6 years ago, this used to be literally the worst thing ever because back then we had everything configured by hand with lovely handcrafted Nagios config files, and people would make changes by SSHing into the Nagios host and lovingly handcrafting their changes and then restarting Nagios and praying. Don't do that, not a good idea. We have moved on since then, and we decided we've got this great tool that we wrote called Deployinator. It's open sourced, it's a little web interface that has these buttons that you can click to deploy things, and you can wrap whatever logic you want into those buttons. So we have this common interface, this common tool that we use across Etsy to do deployments, and we said, we can deploy Nagios this way as well. We started using templates, we stopped handcrafting our Nagios configs, and we said, what if we used Chef as our single source of truth to figure out which hosts need to be in Nagios? So when you test this, when you run this build and test configuration button as the first step of the deploy process, it runs a Chef recipe that does a Chef search, and it finds the nodes that are currently in Chef, and it compares that with what hosts are currently in Nagios, and then it will generate or remove configuration files automatically instead of us having to say by hand which servers we want to have. We also do things like automatically generating host groups based on Chef roles. We wanted to give people some chances to make sure that their configurations were working before they started this deploy process, though. We did this by way of our try library, which is something else that we use pretty commonly across deployments at Etsy. So when you make your changes, now you are making local changes on a development VM that you have, and you run this try Nagios. And what it does is the try library lets you get a diff of your changes, ship that patch over to our Jenkins servers, and because the Nagios binary is nice and lightweight and small, we can have that exist on the Jenkins servers and use it to run the built-in Nagios-V configuration checker. And it gives us the results of that, and it then tells you whether or not it succeeded. So we can see here that there's a couple warnings that we might want to look into, but it tells us that it has validated the config across all of our data centers. So I mentioned we have 3 actual data centers. We have a 4th data center that is the office because we have a Nagios instance running and monitoring the few pieces of hardware that we have in the office. So we have 4 data centers, and this try library allows us to pretty much automatically verify that the config will be valid not just in one data center, but in all 4 of them, because that was something that we had run into in years past, where somebody would make a change in one data center and then it would break in the other ones. It's all well and good to make sure that the configuration is valid and the syntax is correct and all that, but we wanted to go a little bit farther. So my colleague Ryan France wrote a gem that he is in the process of open sourcing called Nagios Validate that allows you to set up custom validation, and we're using this to encourage good Nagios hygiene. So at the end of the try Nagios run, Nagios Validate runs. And you can see here it says validating that modified definitions are not missing contact group definitions. This is important because the way that we use Nagios, we have a template that means that if you don't specify a contact group, it will page ops. It'll use that contact group. Because we're ops people and we're a little bit paranoid and we're like, oh God, what if we miss something? That would be terrible. So we defaulted to paging ourselves. But as more and more people started using Nagios, different engineering teams will set up their own on-call rotas, which is great. We encourage them to do that, to own their own uptime and availability. We found that not everyone was aware of this default setting in the template, and ops started getting paged accidentally more than we would like to. So with Nagios Validate, if you don't specify a contact group, it will now warn you And it'll say, hey, you're gonna page ops. Are you sure you wanna do that? We debated having a little clippy pop up and ask you, but that seemed like too much work on the command line. So now you can still push out a deploy with an empty contact group, but it'll warn you. So we're trying to encourage people to make this explicit rather than implicit. And again, because this is something that we can customize, if we run into other issues that we would like to check for before we have people deploy changes, we can just add those with this gem. Another thing about our deploy process is adding hosts. And I mentioned that we use chef search to add hosts. This used to run every 10 minutes, and any host that had been built within the last 10 minutes, chef would run. It runs every 10 minutes, and it would just deploy those new hosts, whether or not they were actually ready to go into Nagios. That wasn't super great, so we decided to do a couple things. We added in this information. We're now making it visible, so it will tell you, hey, these hosts are going to be added. It tells you who built the host. We have metadata from our host provisioning system, so it says, okay, here's the person who built the host. It tells you the chef role and the cobbler profile that were used just for a little additional information and context about hosts that you're adding. We had it stop adding and deploying Nagios automatically every 10 minutes when chef ran, so it now does this only when people specifically do a deploy in Deployinator. And we also decided that we were going to have hosts automatically go into downtime in Nagios when they get deployed. Now at this point, I feel like I should clarify what it is that I mean by downtime. In Nagios, you can specify that that hosts or services will go into scheduled downtime. So if we need to reboot a host for like a glibc vulnerability, not that that ever happens, we can put the host into downtime in Nagios before we reboot it so that it doesn't freak out in pages and be like, oh my God, the host is down. And we're like, yeah, I know it's down, I'm rebooting it. Like, calm yourself. So when I say downtime, I am talking about periods of scheduled downtime in Nagios, not about us taking Etsy.com down. We try and avoid doing that as a general rule. So Deployinator now puts hosts into downtime when they get deployed until noon Eastern time the next business day. There's a Ruby gem that somehow magically handles that date math. That's pretty cool. And it will also, for more visibility, tell us in IRC that the host has gone into downtime and who built the host. So yes, we use IRC. We're not cool enough to use Slack. We have a whole bunch of IRC bots. It's just lousy with robots telling us information about things. So they tell us, like, hey, this box got deployed into Nagios, and now it's going into downtime. We also have robots now tell us about when this downtime in Nagios is going to expire. Because we have this metadata from our provisioning system, and it puts the downtime on behalf of the person who built the host, it will also remind the person who built the host that that downtime is going to expire, because we have so many different people working on Nagios that the person who built a given host is not necessarily the person who deployed that change. Somebody could make a change to a configuration file, they could add a check, they could edit an existing check, and during that deploy, they could end up bringing in a whole bunch of hosts built by various different people into production. So we wanted to make sure that the people who built the hosts are the ones getting annoyed by them. We're also big into chat ops, so we have a few more Nagios integrations that our little IRC cat knows about. We can set this scheduled downtime for either hosts or services. We can cancel it, we can extend it, you can even leave a comment if you want to be super nice to your coworkers and say why you are scheduling downtime for something. And you can see the status of something. So it'll say, oh, Elasticsearch is critical, but everything else is fine. So go worry about Elasticsearch, but everything else, probably cool for now. And because we're doing this all in IRC, we have a lot of visibility into what everyone is doing with Nagios. One more thing that we do in order to make it easier to deploy changes to Nagios is something that is called perfnag. My colleague on the performance team, Allison McKnight, gave a great talk about this at Velocity last year. Perfnag is a little GUI that lets you set performance alerts and lets you configure those You can see a graph and you're like, oh, I would like to get alerted if this graph does something I don't like. So it will recommend warning and critical thresholds for you based on some SLAs that we have set up. You can zoom in and out, drag and drop those thresholds to see how many times this would have alerted in the past to make sure it looks the way you want it to. And then with one button, it generates the Nagios config for you, copies it into your buffer, and all you have to do is then go and do the try and deployinator combination. So this allows people who work with performance on product teams who are less technical and don't necessarily need to know the ins and outs of Nagios configuration to set up Nagios alerts. So with this, we can be pushing our Nagios changes to prod with more confidence that we are not going to break things. Credit and blame for this particular slide can go to the awesome Alice Goldfuss. So now we're moving through our hypothetical day in the life, and you've built your servers, and it's getting to be lunchtime, and you're all set to go get a sandwich or something, and then you get paged. That's always annoying. You just wanted to eat a sandwich, but we're trying to find some ways to make getting these alerts a little less annoying. So one of the biggest issues that we had, and one of the complaints I hear frequently about Nagios, is its interface. You go to Nagios in the browser, and it's ugly, and it's 90s, and you're like, why am I looking at this? Could you not just put some Twitter Bootstrap on it? That would be an improvement. So with the help of Twitter Bootstrap and my dear colleague Laurie Dines, he wrote something that we call Nagdash. This is also open sourced, and it aggregates all of our Nagios instances. I mentioned that we have 4 of them. It aggregates all of that information together. So if you want to get a look at the state of all of our infrastructure, you don't have to go to 4 different Nagioses or Nagii and go deal with 4 of those terrible, terrible interfaces. You can just go to one slightly less terrible interface. This is a lot of red, so let's not look at that. Let's look at some cats instead. As much as Nagdash worked for us earlier on in Etsy's use of Nagios, it hasn't aged terribly well. So I mentioned that we have more and more teams having their own on-call rotations, setting up their own alerts in Nagios, and Nagdash right now doesn't support that very well. So all of the red that was on the previous slide that I'm sorry if that was terrible for any of you to look at, I know, red, salmon, not good colors to see. Most of those servers actually were not things that would page the ops team. So we as the ops team would like to say, what are the things that are currently wrong for our rotation? What are the things that are currently going to be contacting us? So maybe in the future we'd like to enhance Nagdash to allow us to filter by contact group or something like that. There's also, I on purpose did not make that screenshot an animated GIF because there is a blink tag that happens if a host is down. Maybe we should get rid of that because that's super fun. Another way that we are trying to improve our alerting is by use of Nagios Herald, which is a tool that we wrote and open sourced that allows you to add context to Nagios alerts. So everyone's favorite alert to get, disk space. Who here loves getting paged by disk space alerts, right? One of the things that you might want to know if you get a disk space alert is, okay, is this filling up slowly and did it just happen to go over the threshold? Or is something filling up the disk really, really quickly and I should probably get out of bed and deal with it? So Nagios Herald allows you to add that as context so you can pull in, for example, this ganglia graph. You can add any additional information. We also do things like add who the alert got sent to, how often this particular alert has fired in the past week. We can add additional notes, like a link to a runbook, which is usually helpful for more interesting alerts than disk space. So this is allowing us to specify any kind of context that we want. Nagios Herald works by having formatters that do various formatting things and message classes for things like email versus IRC versus text message. Now, Nagios Herald is a Ruby gem, and it is open source, which means that the formatters and message classes that it has are also open source. But we said, what if you had a formatter or a message class that you didn't want to open source? Or maybe your management isn't so fond of you open sourcing things, in which case, I'm sorry, you should come work for us. Or maybe you had something that was so specific to your use case that you didn't think it would be super, super valuable to clean up and put upstream. So Nagios Herald now supports custom formatters, custom helpers, and custom message classes. And when you are running Nagios Herald, either setting this up in your Nagios config or running it on the command line, you can now specify the locations of these directories, any one or all three of them, and it will do some Ruby magic and let you use now both the built-in formatters and message classes and helpers that come with the gem, as well as your own ones. We've done something pretty interesting with this at Etsy recently. We are using a new formatter and message class that we wrote called Telegram to allow us to kind of customize who is receiving Nagios performance alerts with a little more granularity. So as a background to this, I mentioned that different teams like to get performance alerts on the projects that they are working on, usually 1 or 2 pages. Previously, though, the way that they did this was by signing up for the Perf Alerts mailing list, which meant that they got every single performance alert for every single page, and then they just set up a bunch of Gmail filters to filter out all of the ones that they didn't want, and it was kind of terrible. But as I've mentioned, these people are not they're not technical, but they're not operations engineers, and they don't need to know the ins and outs of Nagios configurations in order to do their jobs. So what we did is we wrote this little page that we called Telegram, because naming is hard and I didn't really want to call it like Nagios Individual Alertinator, which would have been in line with Etsy's naming schemes, but it's a bit of a mouthful. And there's some nice autofill, autocomplete, and people can just type in which pages they want to get alerts for. This is part of our internal staff directory. It saves this to a little database, and then Nagios Herald comes along and says, who else is subscribed to this alert? I'm going to add them as an additional contact, and now people can sign up for individual alerts. Because as much as we've tried to make the Nagios deploy process better, it's still not super fun, let's be real. So we have all this customization with Nagios Herald that is allowing us to add more context, more information to our alerts, to make alerts that are so easy to get that even your cat could respond to them, but don't put your cats on call, they will not actually respond to alerts. So now you're done dealing with this alert that you got, you've gotten your lunch, and you realize that as an on-call person, you would really like to be able to track the alerts that you're getting because you like graphs, and graphs are awesome. So with Ops Weekly, you can do this. This is something else that we've written and open sourced. One thing that it allows us to do that we really like is to generate these on-call reports. So each week, the person who is on call will go and they will tag and categorize each alert and say, was it actionable, was it not actionable, and why? Kind of like the Google form that we saw on Monday asking, was this alert useful to track down and to diagnose an actual problem? We wanted to know if the alerts that we're getting are things that people are actually taking action on. So this is how we figured out that new boxes getting deployed into Nagios without being in scheduled downtime in Nagios was causing us a lot of unactionable alerts, so we were able to fix that. We also have sleep tracking. We've got jawbones that we wear on an opt-in basis. There's a little script that we can run to put that data into Graphite and then generate sleep reports, because we care about our on-call engineers, and yes, people are going to get woken up. That's not super fun, but we'd like to make sure that people aren't getting woken up too much, that the number of times and the amount of sleep that they're losing isn't going up and to the right, because some numbers are good to go down and to the right. So we like to have this information available so you can, go to your manager and be like, hey, look how much sleep I've lost. I need one of those 3-day weekends we were talking about. We have per user reports that you can see. So we've got like heat maps of when you get alerts. For some reason, I never seem to get paged between 7 and 8 in the morning. So I know that if I want to keep up with my FitOps when I'm on call, 7 to 8 in the morning is a great time to work out, because for some reason I just don't get paged then. I can see how my on-calls have been over time to see if they're getting better or worse. And we can do that on a team-wide basis as well. So we can see that over time, the alert volume has been trending downwards. It was pretty bad near the beginning there. Let's not talk about that week. But we can see that, for example, the percentage of alerts that were actionable is still pretty variable. So if we are going and prioritizing the work that we want to do as a team around our monitoring and alerting, we might decide to say, let's look into making our alerts more actionable. So Ops Weekly is a really great thing that allows us to figure out what's waking us up so we can prioritize what we want to be working on. And now finally, it's the end of the day and you're getting ready to go home and you say, it would really be nice if I knew if something was going to wake me up tonight. I mean, the dream is obviously to not get woken up at night, but knowing if something is going to go wrong would be a step in the right direction. So you ask your Magic 8-Ball and it says try again later, Outlook fuzzy, something like that. Not super helpful, but we decided that we could actually make things a little bit better. So I mentioned that we were using Ops Weekly to track actionable versus non-actionable alerts, and we realized that a lot of alerts were not actionable because downtime was either not set or it had expired. And so some known issue, like maybe there was, again, we run on servers with hardware, and sometimes that hardware has to be replaced. And so we're like, okay, we know that this box is down because it's waiting on like new SSDs. Just shut up and don't alert on it. So we put it into scheduled downtime, but sometimes then that downtime expires and pages people, which is annoying enough in the middle of the day, but it's even more annoying in the middle of the night. So we had a monitoring hack week last year, and we wrote something that we called the on-call bedtime story. So what this is it emails the on-call person at 5 p.m. their local time. It knows about time zones and where we each work. And it says, here's everything that is currently in downtime in a not okay state in Nagios, where the downtime will expire within 24 hours. So here are things that currently not alerting because of the scheduled downtime, but they will start alerting within 24 hours, such as overnight when you're trying to sleep. We have things like the author of who set the downtime, whether that was somebody setting it in the Nagios interface itself, or via IRC-cat, or with the automatic downtime from Deployinator. If somebody left a comment on this, it will say what the comment is. So now you know like who to talk to, and if they were nice enough to leave a comment, you might know even why they put the box in downtime without having to go talk to them. So in this case, I was able to say, oh, this is one of our Elasticsearch servers, it needs new SSDs. Obviously, those aren't going to get fixed overnight, so I'm just going to extend this scheduled downtime for another week until those SSDs come in. This also has given us more visibility, so one of my colleagues, Patrick, got this, and there are a lot of performance alerts here, and he said, wait, we're not supposed to be getting performance alerts on ops. Why are these here? So he was able to say, oh, Kristen wrote these checks. Go talk to Kristen. We figured out that something with our templating wasn't working right, and so he was able to avoid getting these like 15, 20 alerts overnight because he got this bedtime story that told him, and he was able to fix them before he left for the day. There's also an on-call bedtime story webpage where we can see everything that is currently in downtime that still has issues. So I can, sort it by who set the downtime and say, here's everything that I put in downtime. I'm going to be a good on-call citizen, and I'm going to go fix those things. So now, at the end of the day, we can go to sleep knowing that if we do get woken up, at least it won't be because some stupid downtime expired. To summarize, old monitoring system, new monitoring tricks. Nagios is really good at one thing, and that is like running checks and getting their results. You can argue about how good it is at that, but we find that it is actually very useful for that, but we want to decide then how we can take those results and make them most useful to us. And this is where it's all about customization, because what is most useful to us at Etsy won't necessarily be the most useful to you. We found out that we had a lot of issues, for example, with machines coming out of downtime, but that might not be your biggest problem that you want to tackle first. Some of the tools that we have, we've got Chef and this try library and Deployinator for better deployments and this automatic scheduled downtime. We have Nagios Herald that we use for context and these custom alert subscriptions. We have Ops Weekly to track sleep and alerting trends, and this on-call bedtime story to help us get a little more sleep. Most of these are open sourced. I will post slides that have links to the projects that we have that are open source. And I think the most important thing for us is that we are always iterating and improving on this. You know, there was the thing a few years ago with hashtag monitoring sucks, and we didn't just say, okay, our monitoring sucks. Well, I guess we're not getting sleep forever. We also didn't fix all of these issues all at once. We didn't like sequester ourselves away for a couple quarters and say, we're gonna fix all of monitoring and alerting. So as we figure out which things are the most painful, as our infrastructure grows and changes, we're able to, you know, develop more of these tricks. Nothing is going to be 100% perfect out of the box. Anyone who says otherwise is selling something. But we are focused on taking the tools that we know, that we already have, and we're focusing on composing them together, on making things pluggable, and on making things customizable and customizing them to work best for us. So hopefully you can take some of these tricks and use them as inspiration to spiffy up your own monitoring tools. Thank you.
Hi, I'm Eric Silva and I work on Google Stackdriver. So what is Stackdriver? So first, Stackdriver is part of Google Cloud Platform. So with Stackdriver, you can gain visibility into services running on AWS and GCP side by side, as you can see here. So Stackdriver integrates monitoring, logging, and diagnostics. Today I'm focusing on monitoring. So we support open source agents like CollectD for metrics, FluentD for logging. These are agents with a lot of community support. We also give you custom metrics so you can monitor things specific to your application. We integrate with PagerDuty, Slack, HipChat, all of those things for notifications. You can see in the bottom left here, the on-call schedule is appearing. So we have built a lot of some great capabilities to help you sleep. So, of course we can alert you if one of your web servers goes down, but you probably don't want to be woken up in the middle of the night because of it. So you can fine-tune your alerting policy with Stackdriver. So what I'm showing here is an alerting policy that applies to a group of resources. So this is a group we set up in Stackdriver, and maybe it's 10 VMs or 100 VMs, and these are running on AWS, running web servers. So I can say if 50% of the members in this group violate this policy, and I'm going to say metric, let's say CPU agent is above 90% for 5 minutes, alert me. So what this is saying is if one or two of my web servers is having trouble, that's, don't wake me up. We can deal with it during business hours whenever that happens. But if the majority of our web servers are experiencing a serious problem, then wake me up, because that's a real problem. Someone pushed a bad configuration or there's a bug in the code. This really keeps the signal to noise ratio high in your alerts, which I'm sure everyone in this room is trying to make happen. So when there is an issue, we offer really rich custom dashboards. We have charts that can support hundreds of time series that are fully interactive, like this one. So if you zoom in here, there's an awful lot going on. So we provided some tools to help you tease apart this data. So we have something called statistics mode that sort of fades out the time series and then overlays things like average, standard deviation, 95th percentile, that kind of thing. We even compute a metric of similarity to help you understand if things are correlated, if they're moving together. We also developed something called X-ray mode, which displays the time series with a sort of translucency, so you can get a sense of density where otherwise it's really hard to see if you have a bunch of bright colors right on top of each other. So here you can see where there are really a lot of time series and where there are few. Now all of this is built on top of Monarch, which is Google's monitoring system to monitor itself. And there is a great talk coming up in a couple of hours all about Monarch, and you guys should definitely attend that. By bringing together signals from monitoring and logging, we are trying to reduce the number of tools you have to use. We hope you guys can get to root cause faster, and we hope you can sleep all the way through the night. Thanks.
All right, enjoy.
Hi. I can't start a talk without saying hi, it's pretty important. So this talk is called All Your Network Monitoring is Probably Wrong. And I think it's really important to start this talk with the one thing I hope you take away from this, if you take away nothing else, and that is my favorite word, greetings. This is the best word in the English language. So greetings, I'm Joe. I like computers. I once had a blog called timetobleed.com. I no longer have much time to blog or bleed, but on Twitter you can find me at Joe Damato. I started a company called Package Cloud, and what Package Cloud does is it allows you to streamline the process of creating and managing repositories of Debian, RPM, RubyGem, and Python packages. We have a really dope SaaS service and an on-premise product, so you should definitely check us out because our software is really dope, and also because supporting bootstrap software is important for the health of the software industry. So anyway, you can follow along. The slides are on the blog at blog.packagecloud.io. So I want to start my talk by talking about a pretty interesting and important idea called cognitive load. Cognitive load refers to the total amount of mental effort being used in the working memory. And I think this is important for us to think about as practitioners in our field, because I think many of you would agree that there's just too much stuff, right? Like there's a lot of different databases, there's a lot of different apps, there's a lot of different libraries, there's a lot of different programming languages, there's lots of different ways of deploying stuff, and understanding how these pieces all fit together, it's pretty difficult, and it takes a huge amount of your time and energy and a huge amount of your brain power every day. And the interesting thing about human beings is that when you're presented with something that's really hard to do, human beings develop sets of coping strategies for getting through them. And I think that one of the interesting coping strategies for dealing with just too much stuff in computing is this coping strategy of copying and pasting config files. And I don't blame anyone that does this. I've done this infinity times, right? You find a blog post or you see something on Stack Overflow or whatever, and you have a bunch of config settings for MySQL or Java or whatever, right? GC settings or whatever, and you copy and paste them and you throw them straight into production and you peel out. And you do that because you just don't have the time. There's just too much stuff to do, and there's just not enough time to do it all, and there's just too much software, right? Not everyone can be an expert in every element of every piece of thing that you deploy. It's just not feasible, it's not possible, it's not realistic. By the way, this idea is actually part of another talk I'm working on called "Programmers Should Get Paid More and Work a Lot Less." Anyway, so cognitive load. Have you ever copied and pasted configuration or tuning settings that you didn't completely understand? Probably. And why, right? Like, there's just too much damn code. Similarly, do you really understand every single graph you're generating in like your monitoring or your graphing situation? Like, I mean, if you just go on your computer and you like apt-get install like Nguyen or collect-d or whatever, you're gonna get a whole bunch of graphs and stuff that are completely auto-generated. Can you really look me in the face as an adult and tell me that you understand every single thing that comes out by default? Probably not. And why is that? Because there's just too much damn code, right? There's just too many plugins, too many files in proc. There's just too much stuff to like really sit down and compute it all out. And if there's too much damn code to configure and tune, because you're copying and pasting stuff off of Stack Overflow, like me and everyone else, what makes you think you can actually monitor any of this stuff? And the spoiler is that you can't. It's just not possible. But the good news is that it probably doesn't matter that monitoring stuff is impossible, but we'll talk more about this later. So, okay, my claim that probably a lot of you would agree with is that the more complex the system is, the harder it is to monitor. But I don't necessarily think that complexity is bad, right? Like, I don't want anyone to walk away from this talk and think that like, oh yeah, this guy hates complexity. Like, no, I think complexity is a fact of life. Like, I think complexity is important. And I can give you a really good example. I don't know how many of you have ever played the cat game. It's a pretty cool game. And I think the cat game is like a great example of complexity because, you know, you want to download and play the cat game on your and phone because your and phone is a small portable electronic device you can use during taxi takeoff and landing. You want to message your buds because you're lonely. You also want in-app purchases because you need to buy more goldfish, you can buy more toys for your cats. You need to do this over a TLS encrypted connection because you have payments, right? This has to happen over a VPN because of China. And you're going to do this while flying because you're bored. And that's like I think that's okay, right? I think complexity, like it doesn't mean complexity is bad. Like you just have, you know, requirements of stuff that you need to live your life and to have fun, and I think that that's fine. But on a more serious note, like two complicated things that I don't think are necessarily bad. Here's one example, like the interstate highway system in the US, right? It's like pretty complicated, it goes to lots of states, probably a ton of bureaucracy to deal with, manage, monitor, keep it up and running, and it's important, right? Like we need it. The Tokyo subway system, like it's also complicated, but also important. So like, okay, you wanna know one thing that's complicated? The Linux networking stack. And one of the reasons why it's really complicated is because there's all kind of features. Different NICs have different RX and TXQ sizes, limits, defaults, Ethernet bonding, IRQ modulation, N-tuple filtering, receive side scaling, receive packet scaling, receive flow steering, hardware accelerated receives flow steering, generic receive offloading, generic segmentation offloading, hardware accelerated VLAN IDs, hardware accelerated timestamping. You're probably using at least two different protocol stacks like IP and TCP and possibly UDP. And there's all kinds of tuning levers and knobs and everything from top to bottom. And there's all kind of bugs. And most of all, there's basically, literally, actually, really, no docs for anything. In fact, there's so little documentation about how any of this works that there's this really, really dope mailing list post that I found on the internet. Check this out. Someone sent this question, a pretty reasonable question. How can I find out the procnet info, e.g. softnet stat is for what purpose? Softnet stat's a really, really, really useful file in proc, but it's like really, really cryptic. Oh, I forgot to hit next, yeah. It's really, really cryptic because it's just not documented at all. There's no names for any of the fields. It's just really hard to understand, right? And the response by the person subscribed to this like, you know, really intense like Linux mailing list, the response was, well, much of this is only well documented in the code. Here is an attempt at interpreting softnet stat. No guarantee that it is correct. Read the code. And in his message, he goes on to say, like, okay, there's this thing called total that gets output in softnet stat, right? And it's the number of packets, whatever. There might be some double counting going on. I think the intention was that these were originally on separate receive paths. Who knows? If you're interested in like the full networking situation, I wrote a blog post about it. It's literally 90 pages long. It's literally everything about the Linux networking stack you need to know, and it is literally available here at bit.ly/linux-networking. You should check it out if you need to know anything about networking. Anyway, I think that that's actually fine. Like, I know I'm probably in the minority. Like, I think it's actually fine that like this is kind of bizarre, because as long as we're just honest about like the operating constraints of the world, like I think it's okay if things aren't perfect, as long as we can be honest about like the state of the universe, right? So tarot cards. These are important because as I've learned from starting a company, you need to be able to see into the future very regularly. And it's kind of hard without these. So I'm going to see into the future right now, and I know that at least one person in this audience is currently thinking that like random operating system has a better, faster, leaner, whatever networking stack than Linux, right? Like Plan 9 or whatever. And I just want to say that that's easily the most boring thing I've ever heard in my life. Anyway, so complex software, it's not necessarily inefficient, it's not necessarily bad, and I mean people expect a lot of complicated features, right? So there's a lot of code needed to support all this random stuff you want to do. See also the cat example. The bad news about complex software, right, is that you're supposed to monitor this complicated code, and then you're supposed to look at some graphs, and then you're supposed to know the answer. And this sounds pretty difficult, but it gets better. What if I told you a driver bug caused statistics to output incorrectly in ProcNet Dev? It's a driver called the IGB driver. It's a pretty popular server driver. Probably many of you are using it right now. We're using it right now on our machines. The driver stats are updated via a timer every 2 seconds. Reading stats via ProcNet Dev produced stale statistics, but not if you read those statistics via ETHTool, which I'm going to mention shortly, because ETHTool uses a different code path. You can fix this by forcing a stat update whenever stats are read by modifying the driver and then redeploying the driver in production. I saw this in production, maybe you did, maybe you didn't, but what's interesting to think about, right, is that like this driver made it into production kernels with this bug in it and no one noticed, because maybe that means that no one actually cares about monitoring networking stuff, right? Like if anyone cared about it, like maybe it would have gotten caught before it made it into production on millions of servers in an Ubuntu kernel or whatever. Then again, it only matters if you're monitoring your network stats more often than every 2 seconds. And like maybe you aren't because you don't care, and that's probably fine and you're probably right, and I'll talk about that later. But if you do care, here's a picture of your future status. Your future status, if you care, is you need to notice a problem in your graph, start reading your stats, collecting code and plugin, whatever, realize the bug's not in your stats collecting thing, read your driver code, realize the bug is in the driver code path that ProcNet Dev hits, write a patch to fix it, rebuild the driver, and deploy it everywhere. Greetings. That's a lot of work just to monitor bytes sent and received, which brings me to a really, really important list that I'm going to share with you. List of things that don't exist. Descending order of probability that doesn't exist. The thing that definitely doesn't exist, free open source software, not real. The and singularity, and then calorie-free chocolate-covered bacon, and so on. So I know what you're going to say next. And what you're going to say is that, okay, like ProcNet Dev doesn't work, but Joe, my DevOps are the literal strongest, and they doesn't afraid of anything. To which I will say, I'll just use the ETH tool. The ETH tool, for those of you who never use it, is a command line tool. It uses the ioctl system call to talk to network drivers. And not all drivers actually implement the interface. The ones which do generally do it differently. So what if I told you that when you use ETH tool to output driver stats, there's no standardized way of outputting those driver stats. Some drivers don't even implement the interface at all, and the ones which do use different field names. You probably wouldn't believe me, and that's fine because I'll reply by saying, oye, dale comparemos. And I think like a good tip is like always have a slide in Spanish in your talk. The best part about this one though is like I'm waiting for someone to slide into my mentions like, yo, who's this guy Dale and what's up with this new Linux tool called Compare Mose? Anyway, so we can take a look at the EC2 VIF driver, the IXGBE driver, and the IGB driver. The EC2 VIF driver, if you run ethtool-s on it, you get a single statistic, RX, GSO, checksum, fixup. What even is RX, GSO, checksum, fixup? I could tell you, but I would need like another hour. So in the words of my Italian-American family currently watching my talk from New Jersey, forget about it. So let's check my IXGBE driver on an AND real computer. ethtool outputs approximately 377 statistics. Here's a bunch of them. That's cool. Of those 377, this is going to be a real surprise, none of them are RX, GSO, checksum, fixup. All right, let's check the IGB driver on an real computer. ethtool outputs 112 statistics. Similarly, of those 112, none of those are RX, GSO, checksum, fixup. But the IGB driver and the IXGBE driver are both written by Intel for Intel NICs. So surely, two Intel drivers will output similar statistics, right? Like it would just be really weird if the same company wrote two device drivers for similar NICs that outputted different statistics. So if we diff them, the diff between them is only 316 different statistics. And it gets better. Some of those statistics are measured in the driver, some of them are measured in hardware, which is fine, right? Like you're probably going to stand up and start screaming, monitor all the things, which I think is terrible advice, by the way, but you'll see why shortly. So okay, let's monitor all the things, right? One of the AND things is this statistic, RX no DMA resources, which like if you're a device driver developer, you can probably guess what that means, right? So that's maybe not that weird. Non-EOP disks, all right? OS2 BMC RX by BMC. It's fine. Because probably what you're going to say to this is fine. I'll read the driver source. I'm really good at the kernels. All right, so let's check out the driver source. Pop open the driver source, try to figure out what the deal is with this RX no DMA resources, and this is what we find. This little loop thing that jumps in here and does a read on something at the very end. If you see at the end there, it says it's doing a read on something called IXGBE QPRDC. What? IXGBE QPRDC. You know what this reminds me of? This reminds me of like those towns in Wales or whatever, where the where the name is like as long as the stage or whatever. Anyway, so what that code's actually doing is it's doing a register read, right? So this driver, like many others, gets a bunch of its stats from the NIC itself. It does this by reading register values. So if it's reading some stuff off the hardware itself, right, like presumably we can look at the documentation, the NIC datasheet for this thing, and find out what QPRDC actually means, right? So all right, here we go. This is the datasheet for the Intel Ethernet controller X540. It is a mere 1,260 pages. Once you plow through your scroll wheel and make it down to page 689, you can find this right here. QPRDC apparently means Q packets received drop count, and helpfully Intel has specified the 3 cases in which packets can get dropped. My favorite is the last one, which is packet size is larger than RLPML, while RLPML_EN is set in the RxDCTL subscript N register, which definitely means something to someone. So success, right? Like this is dope. All you have to do as an operations person is spend the rest of your life repeating this process. Just get the driver code, read it for every single statistic, figure out if the statistic is in software or hardware. If it's in software, read the driver and figure out what it means. If it's in hardware, read the data sheet and figure out what it means. Then graph it, then figure out what the graph means, and you're done. Greetings. What if I told you, though, that Some of these stats aren't even documented in the datasheet. And in those cases, there's really nothing you can do except literally guess. You could email the device manufacturer. Good luck. I don't know if many of you will get this reference. This is from the video game Star Fox. Before you go on the mission and like the talking dog is telling you about invading a planet or whatever, like right before your mission begins, there's a little robot that comes on that just says, good luck. That's this. Anyway, that's fine. I know you're going to say next. What you're going to say next is, no one cares, Joe. No one cares. No one cares about NIC level stats. It's too low level. ProcNet Dev works on my computer for send and receive. And it has high-level summaries of other stuff, like errors, drops, FIFO, frame, compressed, whatever. That's cool. But what do errors, drops, FIFO, frame, and compressed even mean? Well, if you look at the kernel source for ProcNet Dev, you can see this code that outputs the statistics for each of those fields that you'll see in ProcNet Dev. And if you notice, it might be kind of hard to see because it's kind of small, but some of the fields are actually outputted by combining other statistics fields, right? So there's like a few of them that are actually adding a bunch of other fields together and outputting them as a single number. So ProcNet Dev actually, all those fields actually come from the driver itself. Some of the fields that it's outputting in that nice file for you, some of them are from software and others are from the NIC, right? So, and some of the fields are sums of other fields. The good news is that this reduces your datasheet search space, right? Like, just search for the fields you care about, figure out what they mean, and then you can understand what like FIFO, dropped, compressed, and all that means in ProcNet Dev, right? Could be a problem though. What if the drivers don't actually agree with each other on what the individual statistics actually represent? In other words, what if driver stats RX missed errors means something different for every driver you ask? Greetings, friends. The meaning of driver stats is actually not standardized, and so you'll find a lot of cases where driver stats, the actual statistics don't agree between drivers. And BTW, the amazing thing is that stat meanings for a specific driver and device can change over time, meaning that like if you have a version of this device with like, you know, version 1 of the driver versus version 2, maybe they've decided in version 2 to count a specific error a different way under a different category. Which makes your life even better because now all you need to do, right, is just figure out which NICs are in prod for every single box you have, which firmware versions you're using on every single NIC, which versions of drivers are used for each NIC, read all the driver sources for the fields you care about, read the datasheet to figure out what the fields mean, and then build and collect D plugin or whatever to encapsulate this knowledge. But maybe you don't care. Like maybe you don't care about this either, right? This is still too low level. All you care about is protocol level stats. That's weird. Like you don't care. I mean, it's odd because like using ETH-tool properly can eliminate protocol stack problems. Like you can actually tune stuff with ETH-tool to get rid of receive errors, drops, and stuff like that. But whatever, right? Like you don't care about that. That's fine, right? So let's just read protocol stats from ProcNet SNMP, right? ProcNet SNMP, that's dope, right? There's an RFC 2013. The fields are standardized. This is great. It's higher level, so I can figure out, you know, where the protocol layers are breaking down. And most of the stats are gathered in software. So that's much easier than reading a 1,200-page data sheet, right? Like I can just read a bunch of source code and figure it out, I guess. But what if I told you that there's lots of bugs in the way statistics are counted and output in the kernel? What if I told you that there's several cases where counters are incremented just in the wrong place, like we saw in that email that I showed you where there's double counting? There's several cases where there are double counting throughout the network stacks. There's several cases where the counters aren't incremented where you think they should be incremented. Here's an example from a comment in the UDP protocol code. It just says reporting eno buffs might not be good because it's not tunable per se, but otherwise we don't have a good statistic. We could add another new stat, but at least for now that seems like overkill. So who knows, right? Like who knows how these things are being accounted or if they're being accounted in a way that makes sense to you as a user or operator of the system. So if this is an important statistic for you, your monitoring might be wrong, and the alerts you set on that monitoring might also be wrong, which means that you can look at graphs when you have an incident and not know what's actually happening or what's going on. So what does this all mean? It means that monitoring something requires a very deep understanding of how that thing works at a fundamental level. Otherwise, your graphs, alerts, etc., might not actually be measuring what you think they're measuring. And this is why people can build entire businesses around monitoring networks or other stuff. And so I urge people to like resist the temptation of just trying to solve every problem with like a quick bash script that you shave out over the weekend. Because properly monitoring, setting alerts, and so on requires significant investment, not just like a simple script that you can just throw together. I don't think this is necessarily bad. I just think it's important to think about. I think it's important to recognize that monitoring is difficult and it requires time and effort. It means that, what else is this? Means that, nothing is free, but this doesn't mean that software is bad. I don't hate Linux or Linux kernel. I think the software is dope. I just think it's important to be realistic about how it works. So I hope no one will jump to that conclusion. I'm not recommending against using your computer. This is just reality. This is just the way it works, right? And this brings me to an aside. I think an important aside that probably as engineers or practitioners in this space we don't think about often enough. And that aside is this sort of connection between time, money, and business. I think engineers always think that they can solve everything by writing enough software. The problem with that is that sometimes spending your time doing that and writing software actually doesn't make any business sense whatsoever. And other times doing that is actively detrimental. How long would it take you to figure out if all your networking metrics are right, figure out what they all mean, set alerts that are sensible, right? Like remember, you need to probably read a lot of code, data sheets, different versions of different drivers. It's going to take a long time to figure out what this all means and put it all together. Hopefully the blog post that I wrote would give you a jump start, but like there's still a lot of work you have to do on your part. When I was thinking about this, I stumbled across this really cool calculator by the folks at Baremetrics. Baremetrics put together this calculator where you can try to sort of figure out how much will it cost the business to do a particular thing. So for anyone who's never like run a business before, you can check out this calculator. You can put in like, the cost of an engineer salary per year. If you never run a business, make sure to add in 35% overhead minimum to salaries. If you have like, deep tissue massages every day and like free lunch and all that, probably want to add in a lot more overhead than that. But anyway, this is why like the idea that monitor all the things doesn't make any business sense for most businesses below a certain revenue level. Or like if you're a small business, a small startup, you just got up and running, like monitoring all the things doesn't necessarily make that much sense unless like you already have previous experience at a deep level with the things you're monitoring. And this is kind of why it doesn't really matter if these stats are wrong, right? Like this is kind of why probably no one noticed when the IGB driver shipped with a bug in it that prevented stats from being up to date on 1 second intervals, because it just doesn't matter for that many people. And if the stats actually did matter, right, like your business or some business somewhere would invest the time and money to figure that out. So anyway, in conclusion, I don't think complexity is necessarily bad. Even simple software is buggy and hard to monitor correctly. It all just comes down to value and time, right? Your network monitoring is probably wrong, but probably not because of anything you're doing. It's just because it's wrong because the networking stack is complicated, it's hard to understand, and it's hard to internalize. But the good news is that it probably doesn't matter, because if it did, your company would invest the time and resources in figuring it out. I don't know if I have time for questions, so if I don't, and you want to ask me something about computers, I'll be around. So thanks for listening. Yeah, sure. I guess I can take 2 questions if anyone has.
Tied for first ever largest Monitorama presentation, we have Megan and Justin and Dan. Woo!
Good afternoon, everybody. Nope. Slides. Got it. Good afternoon, everybody. Dan, Justin, and myself are really excited to be here this afternoon to talk to you today about Twitter's next generation monitoring and alerting system. So the goals of this 2-year-long project were to improve reliability, to simplify the user experience, and to empower human reasoning. Over the next half hour, we'll share what we accomplished, as well as especially what we learned over the course of those 2 years. Hopefully, this will give you some food for thought as you choose amongst the many monitoring and alerting tools that we've talked about over the past few days. Or perhaps build your own. We won't deep dive into our architecture here, but we'd be happy to discuss it afterwards. Please meet us outside or in our Slack channel. But first, we'll introduce ourselves. So I'm Megan, and along with Dan and Justin, I joined the observability team about 3 years ago. When I started, I was very interested in visualization, but since then, I've become interested in learning more about the user experience of alerting, as well as the challenges of implementing that user experience at scale.
And I'm Dan. During my time on the team, I worked on alerting systems, old and new, but I'm also interested in distributed systems and computation theory and engineering systems that make other engineers' lives easier. I recently joined Google, but these guys were nice enough to let me present with them anyways.
And I'm Justin. I've had a lot of fun working on lots of different parts of Twitter's monitoring stack, but most of my time has been spent working on the alerting service and the visualization front end. Oops. Sorry, guys. So my favorite part about working on this team is actually empowering our users to do their work better. Along those same lines, I'm going to empower Dan and Megan to do their work better by, talking about all the old stuff and saving the fun new stuff for them. So before we dive into the alerting system, I'll talk really briefly about what our team does in the context of Twitter engineering. So the mission of the observability team at Twitter is to provide a scalable, robust, and real-time monitoring infrastructure to our users who are other Twitter dev teams. So practically, this means we provide a means for our users to write, alert on, and visualize their metrics. So the observability team isn't directly responsible for the monitoring of all of Twitter's production services, but rather we make the platform and product that allows teams to do this themselves. So you can say that we're not the watchers on the wall, but rather we build and maintain the wall. So the observability stack looks something like this. I know Katie showed a similar diagram earlier this week, but Twitter runs in multiple zones, which are collections of co-located servers that run within a network, and a stack like this exists in each of those zones. So the lifecycle of a metric begins on the bottom of the screen, where users export metrics, which are all doubles, as JSON on HTTP endpoints on their services. Collection agents sit alongside our users' service instances and pull those endpoints every minute. So they send the metrics to our time series database, which is backed by the Manhattan Key Value Store, and from there the metrics are served to our alerting and visualization services. So again, most of this talk is centered around the alerting service, which is just one small part of this big diagram. But if you're curious about the rest of it, we recently published a blog post a few months ago called Observability at Twitter. I think if you Google it, the first result is the older 2013 version, but the newer one should be right under that. Cool, so now let's talk about the old alerting system we had, what it did well, and why we ultimately felt it needed to be replaced. But first, a few words on scale. In the time since the three of us joined the team, which is about 3 years ago, the number of metrics written to us increased from about 300 million per minute to a peak of about 4.3 billion per minute before we freaked out and asked people to reduce their metrics. I think currently we do about 3.5 billion, which is right around there, yeah. So correspondingly, this increase in writes correlated with an increase in reads. So in its final days, the old alerting system handled 25,000 alerts, which together contained about 3 million monitors running each minute. And with this increased scale and use, the old alerting system began to demonstrate a few shortcomings. So we're going to frame those issues for you in the context of the two different ways that users interact with our platform. The first is the process of writing and maintaining alert and dashboard configurations, and the second is the way that our users interact with our alerting system while on call. So first, alert configurations. So in the old alerting system, we had a pretty straightforward object hierarchy for our alerts. Each alert contained n rules, each of which had m monitors. So a rule is basically a query to the time series database, and a monitor is a predicate applied to a single time series. So alert config files were stored in Git and uploaded to our alerting system via a command line interface. So what was good about this? First, it had a pretty straightforward, simple config language. Second, over the years, a lot of configs made their way into Git, so there were plenty of examples to look at if you were trying to write a new alert. And third, you could quickly write new configs, push them to Git, and upload them to our system. So then what was bad about it? Well, the config language is maybe too simple. The large body of existing examples suffered from bit rot and lack of. It's really easy to write, commit, and push broken configs. The language itself was a JSON-ish, but not really domain-specific language, and it was pretty straightforward, but it was clearly not designed with templating, shareability, or reuse in mind. So to get around this, we ended up stapling on Mustache on top of it to allow some kind of templating, but it never really felt like a complete solution, and even with it, programmatic generation of configs was still pretty difficult. So to get around that, many teams created their own custom alert generation workflows using complicated scripts and templating, leading to a fragmentation of workflows. Additionally, ownership of configs was a problem, and sometimes you'd see an alert or template in the repo that you wanted to use or pull into your monitoring, but you weren't sure if you could safely do so. You'd see a file like this, and obviously your first question would be, does the farming team even plant cherries anymore? I thought they were deprecated. And then you'd git blame the file and ask the author about it, but you'd find out that they didn't work there anymore, and that was bad. So the number of orphaned and unmaintained configurations became an issue. These configs also suffered from a lack of validation. So neither at creation time nor at upload time were the configs validated for correctness or best practices. So we made it really easy for our users to get up and running fast. You could probably go from a blank editor to a running alert in about 2 or 3 minutes, but we didn't make enough of an effort to help them do it correctly. And finally, this is kind of a subtle one, but another configuration shortcoming was that alert configs were completely disjoint from dashboard configs, which were written in a Ruby DSL. And it seems kind of obvious in hindsight, but we realized that it was redundant to require users to maintain separate configurations for these objects when the two of them often operated on the exact same data. This, of course, isn't an absolute rule, but we observed that if your metric is important enough that you want to alert on it, you probably also want to chart it as well. So when the configs were kept separate, a user might add a helpful new metric to their alert, but forget to add it to their dashboard. So it's possible that a user could be alerted for a metric, but be unable to see it in their dashboard when they went to diagnose. Or even worse, a user might accidentally be made aware of an issue in their service by randomly browsing their dashboard instead of having been alerted by it. So once users had alerts uploaded to the system, they faced a new set of challenges being on call and interacting with the alerts. So as mentioned earlier, the old alerting system was one cluster per zone, and this meant it only knew about data from its own zone. Therefore, when that zone would go into a degraded state due to something like a network issue, it was possible that the alerting service would become impacted as well, resulting in missed alerts. And apparently, an inability to alert during service outages is not a desired property in an alerting service. So to get around this, teams would put alerts in multiple zones for redundancy, but they quickly found out that this resulted in redundancy. So in order to protect themselves from zone-level failures, they had to suffer being alerted multiple times during normal operation. Beyond this, there were 2 other issues that could lead to faulty alerting, and the first was that the old system didn't have the best isolation properties. So an alert by a bad actor with 1 or more excessively expensive queries could easily delay the execution of all the alerts running on a particular shard of our alerting service. The second was that deploys were impactful. Alert executions didn't happen during deploys, and those executions were never retried, even after the system came back online. So this led to users losing visibility during that period and potentially not being alerted about issues in their services. Deploys didn't usually last longer than 5 or 10 minutes, but still it didn't feel good for us to cut off all alerting whenever we wanted to deploy new features or bug fixes. So now I'll hand things back to Megan to talk about how we went about solving some of these things.
Thanks so much, Justin. Yeah. So how did we set out to solve these problems? We created a new system that would scale as Twitter grows. We wanted to improve the configuration experience that Justin described, and we wanted to reduce lost visibility due to system issues. So what did we end up doing? Well, the first issue we tackled was the configuration story, and we wanted to simplify configuration to make it much easier to create, tweak, and maintain alerts as well as dashboards. But simplification also needed to be balanced against the need for expressiveness and power, because for us, some of our users are happy with a one-click solution, but we have many power users who really need a programmatic solution to configuration. The main way we achieved simplification was actually by combining the configurations for alerts and dashboards. So now there's absolutely no chance that an alert or dashboard configurations will diverge. An alert is simply a predicate that's placed upon data that you're already looking at on your dashboards. So by co-locating these alerts and dashboards, users no longer need to jump between tooling in order to diagnose issues. All of the relevant information is in one place, meaning faster remediations and happier on calls. Next, we reduced cargo culting by making configurations shareable. So the new configurations are written in Python rather than that janky DSL, and this gives users immense flexibility. It makes it simple for users to follow best practices. In order to do that, we created a shared library that could be easily imported. Now, creating a new configuration is as simple as importing and calling a suite of library modules. For example, if you want to monitor the JVM, you don't really need an in-depth understanding of how to monitor the JVM. You can simply import the configuration for the JVM module, and you're good to go. Choosing Python for our configurations also let us test these libraries and the user's configs. So basic tests are created automatically now for every single config, and they must pass before the configs can be merged. We also layered on top of this a more robust server-side invalidation portion, which protects users from common mistakes. For example, following best practices, or perhaps having too expensive of queries and bringing down other users. Together, these choices have resulted in higher quality and better maintained configurations. So we were improving our configurations, and that was all going well, but we were only halfway there. Without a more reliable alerting service, users still can't trust in their alerts or in the health of their systems. To fix this issue, we began by solving that single zone failure problem. This meant that alerts couldn't be zone local as they were in the old system. Instead, we needed alerts to rebalance during zone failures to a healthy zone. So with this new multi-zone alerting system, users no longer need to deploy their alerts to all zones and be double alerted or lose visibility when a zone is failing. The next problem was dropped evaluations. So now, when an alerting node fails, the new system keeps track of the last successful evaluation point, and when an alert is balanced to a new node, it restarts evaluation from that point. Not only does this facilitate our deploys, so you don't have outages, but it also means that alerts being rebalanced between zones does not cause a gap in evaluation. So together, all of these things mean that users no longer lose visibility, and that means that they can put more trust in the alerting system. Finally, the new architecture of each alerts means that each alert's execution is scheduled fairly. This means that expensive alerts don't starve other alerts. It has allowed us to improve the alerting system's time to detect by about 30%, from 2.5 minutes to 1.75 minutes. And again, this really means that users are going to get alerted faster and be able to solve problems quicker for the business. So I've described a lot of things, but what does the architecture actually look like? Now, there's going to be a lot of lines and boxes on this slide, and I'm not going to dig into each one of them. If you want to discuss the architecture in more detail, we'd be happy to do that after the talk or on our Slack channel. But I am going to walk you through like 3 of the basic moving parts. So the first one is that we have a balancer that assigns alerts to logical shards and rebalances those shards when physical nodes go down. For instance, during a deploy or a zone failure. Each minute, the system checkpoints the most recent successful evaluation, and on startup, resumes evaluation from that point. So this system is designed for graceful degradation. Failures have a limited scope. For example, if that sharding system goes down, work allocation will stop, but it won't actually affect the evaluation of alerts. Or perhaps if the history database was to go away, we wouldn't be writing history data anymore, but it wouldn't impact any of the other portions of the alert evaluation. And again, we'd be happy to discuss this architecture in more detail. If you have any questions, come find us after the talk. So with these improvements to reliability and configuration, we created a more reliable and less frustrating experience for our users. But monitoring is more than just the sum of its parts. The end goal is to help users actually solve problems. So there are a couple other things that we did, and the goal of those was to help solve the problems that come from complex distributed systems interactions. As we've heard before, monitoring isn't unit testing, it's closer to integration testing, and we really needed to make it trivial to reason about the system as a whole and to bring together relevant signals from across the stack. So we began thinking of a way to provide this, and we settled on 3 different types of context. So the first one is global context, peer context, and then local context. And what this meant for us was that globally, users need to know about ongoing changes like site-wide failovers or issues with backbone components like the network. The next thing that they needed to know about was the health of their direct dependencies. For example, is their storage layer struggling? Or is their client not sending them any requests? And finally, they need to know about recent changes to their own systems, such as deploys. By bringing these signals together, we were able to enable human reasoning and improve the time to root cause issues. But there is one more step in responding to alerts. Once you've root caused an issue, you're not done. You need to actually remediate that issue. So we needed to make it trivial to respond to alerts once you determined what the problem was. And we accomplished this by including descriptions, contacts, escalations, and runbooks right in the alert UI. This makes it simple for you to understand what you're looking at. You can escalate to someone else if necessary, and you can follow concrete runbook steps, like the ones that Katie described on Monday. So altogether, these improvements, the goal of these improvements was to empower human reasoning, to bring those signals to the right place. And now I'd like to hand it over to Dan to talk to you about a few of the lessons that we learned.
Thanks, Megan. So now comes the part where we come clean and tell you all about the parts that haven't gone as smoothly as you might think. Problems always come up when making a new project, but they tend to magically disappear when a presentation is being prepared. So that's a shame because a lot of the valuable knowledge comes from those problems and the solutions that people figure out after a lot of hard work. So a big challenge to writing the alerting system was making it distributed. From the beginning, we knew that it would have to be so. We wanted availability numbers that aren't possible without distribution, and we needed this new system to scale horizontally to at least another order of magnitude relative to the previous system. Well, as we've heard from previous speakers, distributed systems are hard to get right, even though exactly how hard depends on the problem. In our case, the system has a considerable amount of state, which is hard to keep consistent. It aggregates data from multiple sources, which can make the logic pretty convoluted. And it also computes data in real time, which requires that it know how to deal with delayed data and excess load. Well, as you could have predicted, distributing the system was the cause of a number of challenges. I'll focus on one in particular, but first, some context. As you know, any system that wants to parallelize work needs some way to divide that work into smaller pieces and assign those pieces to workers. That's called sharding. And how you do that is actually one of the key decisions when designing a distributed system. Here, the work is evaluating alerting rules every so often and taking action based upon that. We chose to shard the alerts by ID and assign them to workers dynamically. That's a pretty intuitive way of doing things, but we could have made quite different choices. Secondly, our implementation relies on existing tools as much as is safe for a monitoring system. It depends on Zookeeper for maintaining consensus, on Manhattan, Twitter's key value database for keeping state, and on Aurora for orchestrating those instances. Designing a distributed system from scratch is a daunting task. At the beginning, all we have is a list of rough requirements, an excess of tools to tackle them, and a blank screen. Lucky for us, people have thought about many of these problems before, so we have a bunch of great advice on how to design our system. Some of that advice takes the form of principles. For example, we should come up with clean abstractions that capture the work that needs to happen. We should minimize the amount of coordination required between those abstractions to keep their interfaces simple. We should parallelize the work so we can scale the system. We should make sure that the load is distributed evenly across those machines so that we can run efficiently. We should also make these decisions quickly and ship a product in a timely fashion. We take, all of us, these principles seriously as engineers, like a code of honor that guides how we write code. If you think about it, we're kind of like knights with our own kind of chivalry that's not sexist. Well, there's one kind of night, or one night in particular that I want to talk about. Jaime Lannister. Jaime Lannister was a knight, maybe the best swordsman in the land. As a great knight, he had a code of honor. He took vows, and he did his best to live by them. He served as personal bodyguard for the king. He loved his family. He protected the weak and was known throughout the land. Now, if you've watched Game of Thrones, you may know where I'm going with this. If you haven't watched through season 3 or read the books, then cover your ears and eyes for a moment because there's some minor spoilers coming up. I left some details out of my description of Jaime Lannister. I didn't lie. He did serve as personal bodyguard for the king until he stabbed him in the back. He did love his family so much that he fathered some kids through his sister. He was one of the best swordsmen in the land and protected the innocent until his right hand was cut off for trying to save a woman from bandits. He was known throughout the land, infamously, by the name Kingslayer. So he sounds like a kind of nasty guy, right? Well, some fans may disagree with me, but I think he's actually a pretty awesome guy. He's just been put in a lot of really difficult situations. Okay, spoilers over. Open your eyes, because you can see this. So you may be thinking, what does this have to do with monitoring? Well, just like Jaime, we have our code of honor, and we've taken our vows. In our alerting system, we have pretty intuitive abstractions, rules and rule sets, where rule set is just an alert by a different name, essentially. So we can chart along those lines, but we have a choice to make. Rules are more compact, uniform units of work. So ideally, we'd want to make the cut there and distribute along those abstractions. But if we do that, the lines cross. That would be bad. Not as bad as total protonic reversal, but it would force us to coordinate a lot between the results of rule evaluations. And that would lead to more time invested and more bugs. On the other hand, if we shard by rule set, we don't have that problem. But then we might have a hard time keeping the load distributed evenly because some rule sets may be much bigger than others. So how do we know beforehand which is the right choice? The problem I'm getting at is that designing distributed systems is a difficult situation. Sometimes it seems like all that great advice on designing them is like the first description I gave you on Jaime. It all sounds great when you leave out the details, but reality comes with a lot of complications. We can get through it, but our vows are going to take a beating, as Jaime himself said. So many vows. No matter what you're doing, you forsake one vow or the other. We have tons of great advice, but in the end, our situation may force us to choose between contradictory tips. When that happens, we have to do our research, buckle down, and take our best shot. As it turns out, the decision we made didn't come out all that bad. We chose to shard by rule set, like I said, to keep the system simple. And that means that the load is not actually spread evenly across the cluster. Some people, as it turns out, really do want to have 20 rules with 5,000 monitors in each one, and we don't partition those. So we could have implemented logic, or we could in the future implement logic to spread the load more evenly, but right now it's easier to just over-provision clusters. Still, things could have easily turned out differently. That's why we didn't want to come up here and tell you how to build your systems. There's lots of people telling you how to do that, and a lot of it is really good advice that's worth looking into. Just make sure that you also remember that it's impossible to avoid making mistakes all the time. And the next time you're spelunking through some horrible legacy project that's riddled with bugs and impossible to read, think about Jaime Lannister before you call the author Kingslayer. So system design is only one of the challenges to software engineering. Another family of challenges is how to give our users what they want. Users are the whole reason we do what we do. Whether we're designing consumer products or making infrastructure, it comes down to the fact that other people value what we're making. When designing and deploying the new alerting system, we had to work with our users extensively to support them as they migrated to it and collaborate them when that path was blocked. We found that even though it's exciting to have a lot of people using our system, sometimes supporting people can start to feel like a burden. After all, helping one user with a simple problem doesn't have the same impact as applying the same amount of time to improving the project. At the same time, some user questions really do deserve a team member's attention. So we set up multiple lines of defense to reduce the amount of time spent supporting users on known problems. The front lines are the points of interaction with users: UI, command line tools, and configuration libraries. As Megan said earlier, we wrote a comprehensive configuration validator to warn users about quirks and frequent missteps that other people would make. We made sure our command line tools usage messages were helpful, which is pretty easy to forget to do, as it turns out. We also spent almost as much time documenting our configuration templates as writing them, and explaining how to use them in the code as well as what they mean in the context of monitoring. Behind the front lines, we placed a suite of user documentation, providing deep links from UI tools and configuration libraries to relevant documentation. We tried to make sure that it covered all aspects of the new system in a friendly way, without obfuscating the useful information. For example, we provide a simple getting started guide, which everyone has nowadays, right? Another guide devoted to explaining the core concepts of the system, a guide detailing best practices to writing configurations, an FAQ, and auto-generated API docs for the shared configuration libraries. The source of the documentation lives next to the code to simplify keeping it up to date, and we try to enforce that documentation changes go into the same review as the code changes. For the third line, we have a dedicated support on-call rotation. Each week, a member of the team dedicates themselves to user support. They're attentive to the chat room and mailing list, answering questions as they come up. By focusing user questions on a single person, we reduce context switching for others on the team. That makes it easier for the team to focus on development when their expertise isn't needed for simple questions, at the cost of dramatically reducing the productivity of the on-call. Aside from day-to-day support, our interactions with users focused on migrating them to the new system. A problem we ran into is that while some people were very excited to try out the new system, a good number of others were not. They were on the hook for other important tasks that didn't line up with our roadmap. So we tried to figure out an answer to the question, how do we get people to do what we want? To start, we took the classic carrot and stick approach. To lure users to migrate, we made the new system better with higher reliability, fewer bugs, and more features in most cases. To drive people off the old system, we stopped all non-essential development on it and set deadlines for people to stop using it. That's not the whole story, though. Lots of people were excited about trying out the new system. They even started contributing to the shared libraries. But some users pushed back. A few did so because they wanted a rarely used feature that was not supported in the new system. Others because migrating was a lot of work and they had more important things to do. It was easy to feel discouraged, but doing that didn't help either of us. What did help us was to rethink our goal. Our goal was not really to get people to do what we want. It was to make Twitter better as a whole. The problem was that by thinking in terms of carrots and sticks, we implicitly cast our users as mules to be lured and driven. But as it turns out, people are really not that crazy about carrots, and they really don't appreciate being hit by sticks. So instead of looking at our users as goals that we had to meet, we had to acknowledge them as the competent individuals they are and reach a mutually beneficial compromise. Of course, that's just the start. Such a compromise usually means committing more development work and dealing with the delays in the roadmap. We certainly didn't want delays, but sometimes they are necessary, especially from the perspective of the organization as a whole. So in the end, making a good monitoring system, or any other kind of system, doesn't come down to a single thing. It's about balancing the needs of users against those of the company and the team and 1,000 other things, in search of an optimum in an incomprehensibly big problem space. The only way to get closer to that goal is to try things, learning from our successes and failures. We hope that we've helped you in that pursuit by sharing our experiences today. Thank you for taking the time to listen to what we had to say.
People have no doubt surmised we are an intelligent DNS company, and we specialize in traffic management and route optimization. And we'll talk a little bit about what that means. So for better or worse, DNS is still the entry point to a big chunk of the applications that are in use today on the internet. We've heard a lot about how the way applications are being built and distributed and deployed has evolved over the last 5 to 10 years, even going so far as to get to serverless and stateless. And that presents a challenge that a lot of you have been discussing in terms of how do you monitor that? How do you wrap your head around performance or success or happiness or whatever your KPIs are? And this one is focused on the other side of that, and that is taking those metrics and making actionable routing decisions and doing something in the real world with that. And so the way we do that is we piggyback off all of you smart people. So you'll see a bunch of logos here for monitoring companies and metrics companies. And rather than reinventing the wheel in our platform, we let you plug in all of these different data sources into our platform, stream that data to us in real time. We beam it out to our edges, and for every single DNS query that we get, we will reflect the state in these systems and respond dynamically based on whatever is appropriate, whatever you've configured. So we're going way beyond sort of up-down, and we're taking into account things like AppDex or connection counts on your ELBs or your F5s or lots of really cool stuff. We get data back out of the system. We've got our Rain Tank or our Grafana.net app just came out last week. And then, if something notable has happened in the system, we have webhooks or send it out to PagerDuty or HipChat or Slack. And then we've got a bunch of toolkits. I think there's more than that, but those are the logos that we were able to find in time. The other thing that we're doing ourselves is Pulsar, and this is a telemetry-based routing engine that uses, sort of in its nominal form, we've got a JavaScript tag you can embed on your website, and we'll make measurements from your actual end users to your data centers or your content delivery networks or whatever, or you can bring your own data, which I think is a really interesting point. And send that to us. Again, we get it out to our edges, and for every single DNS request, if you open the Yelp app on your phone right now, for example, that hits our data centers, and we say, oh, this user is on Verizon Wireless in Portland. Even though the Seattle data center is closer, we should really route that user to LA because there's some network congestion or something like that. So we're combining this sort of outside-in telemetry with inside-out stuff that you're pushing to us from all of those different vendors that we kind of looked at. And the way we enact all of this is with what we call the filter chain. And so we've got an example one up here on the left. And so filters are little programs that you just attach to your regular RFC compliant records. Every single query that we get runs through the filter chain, and then what comes out the other end is sort of the optimally computed answer based on all of the data feeds that you've got coming into us or the monitoring that we're doing or Pulsar. So if the internet gods are willing, we will attempt to just show you how to do one of these, and we'll build a simple content delivery network. So I've got an example record here for Monitorama, and we've got 3 data centers configured here, and does that read? That is not even close to readable. Let me see if I can make that bigger. So if I query this record, man. We see that I'm just getting the answers based on the order they're entered into the portal. And so we're going to add a filter chain to this. And so the first one we're going to do is we're going to add this up filter, and this might look at some information coming out of Datadog. The next thing we'll do is a geo-target filter, and so we'll sort the answers by proximity, and then finally we'll just do a select first n, which will, it's like the head command in Linux, and just returns one answer. So we save that, I return back here, and in real time that change was pushed out to the edge, and this host is in New York, so that's where we're being directed. If there's any kind of failure detected by our monitoring system or catch point or whatever you have plugged into this, and the server goes down. Again, in real time. And now I'm going to be redirected to San Jose, which is the next nearest data center. And so this is how you kind of build, that's a simple content delivery network. You can plug in load shedding metrics to deprioritize answer based on their current connection counts, things like that. You can add pulsar in to, in addition to that, do sort of the quality of service Waze type routing. And yeah, that's it. Any questions? Are we good? No questions? No time. All right, thanks everyone.
Beautiful. Good afternoon, guys. My name is Stefan. I'm with a company called Sumo Logic. Quick show of hands, who here uses a log analytics tool today? Okay, as expected, most of you. Who uses a metrics product today? About the same number. Who uses a product that does both in one product today? Okay, not very many people. Good. So quickly about Sumo Logic. We're traditionally a SaaS-based log analytics product. Been around for about 5-6 years, built in AWS for people predominantly who consume cloud and build applications in the cloud. We have functionality like sort of what you expect from a log management product. Search, you can build dashboards on top of logs. You can do Lifetail, some basic analytics capabilities. At this point, we have about 1,000 plus paying customers. And we're kind of undertaking the next step in our evolution. So we no longer deem ourselves a pure log analytics company, and we're about to launch sort of a second big product under this platform that's going to make us, as marketing calls it, a machine data analytics company. What they really mean by that is we're basically adding time series capabilities, metrics capabilities into the same product. So once you have this, you can build dashboards like this, where the bottom two panels are based on log data, and the top two are based on time series data. And I want to spend a couple of minutes talking to you through some of the design decisions we made and kind of why we think it's a good idea to combine the two products. So this is kind of par for the course, but probably bears mentioning. We wanted the data, the time series data, to be self-describing, meaning tags or labeled. So we kind of built a platform around that type of data, knowing though that a lot of the data out there is in graphite format or similar formats where there's no self-description and the tags are missing. So we added some functionality that lets you on ingest label the data. So you understand your graphite format, but we don't. And with these rules, you can basically teach us, the first thing before the dot is the host, the second thing is the cluster, and so forth, right? And then sort of everything follows a similar schema, right? We also don't prescribe to you that you should have hosts because, serverless is kind of the term of the year. We will probably later give you means of teaching us containment. So you can say, okay, a cluster contains hosts, which contains processes and so forth. But for now, it's just sort of tagged values. We have already added support for a couple of different formats to send us log data. The most fundamental one being graphite. We also can collect from a couple of other sources, including AWS CloudWatch, where we go out and pull the data in, so you don't have to install any agents. The collection can be done in a variety of ways, either with our agent, the same agent that already is used to collect logs, or sending it straight to our endpoint in the cloud, which is also an option for the logs. We're also, and this is not going to be sort of in the first release of this, so anything that has an asterisk up here is going to come later this year. We're going to pull in additional information that isn't in your metrics, like AWS tags, and we're going to add them on ingest to your time series. So then, instead of an AWS instance ID, you get things that make sense to you and that use to label your instance in the logs and metrics both. We're building a feature that lets you turn logs into metrics, and you're going to be able to do that in two ways. One, you have logs where there's a numeric value somewhere in the text of the log, and you can just parse that out. And the other one is more interesting. You can do aggregates over your log. So you want to count each minute how many 404s you got in your web server log. You can turn that into a data point in your time series. And then you get all the benefits of having time series without necessarily having control over the log format that you ingested. Another thing we're working on is sort of these tags or key value pairs that you add to your metrics. You will also be able to add to logs we ingest. You will have a singular model that organizes both your time series as well as your logs, which will enable you to very quickly basically go from a log on a host to the relevant metrics on the host, or the Lambda function or the Docker container, right? And finally, we're going to do what we call unified alerting, and once again, it's alerting based on both thresholding in your time series as well as events in your logs. So you can parse something out of a log and trigger an alert based on it if it crosses a threshold. That's really all I had. Thank you for listening. Find me in the hallways if you have questions about this or want to try it out, or on the inner tubes. Thanks very much.
Let's give a round of applause to Joey.
Good afternoon, everyone. I'm Joey Parsons. I'm the engineering manager at Airbnb, engineering manager for site reliability at Airbnb, and I'm here to talk to you a little bit about how we do monitoring for both our systems and health. So I'll take you on a little story about a little bit about my life, but first I want to talk about a moment that I had the other night at Pips and Bounce. So while everybody was playing ping pong, I was taking a look at all the attendees around, and I looked at my cell phone, and I was looking at just kind of my home screen, and I was thinking that every single one of these great companies is powered by a lot of the work that goes on by the folks in this room and our friends back at home. There's so much beyond kind of product market fit that goes into these companies, and a lot of it's done by all of the great developers, whether you're writing books, writing code, writing blog posts, all these sorts of things to make these companies really work. I know I personally wouldn't be here and wouldn't have the career that I have today without the efforts of a lot of people in this room. I've learned from every single one of you, so I wanted to say thank you to everybody and give a big round of applause. So one of the other reasons I love Monitorama is because I've absolutely fallen in love with the city of Portland. We actually have a small engineering office here in Portland, as well as our main customer experience office. And one of the really cool things about it is there's a really fucking awesome bear shark in that office. I'm not quite sure what the origins of it or what it means, but if you go into the office and you see a bear shark, it's, nothing can beat that. So this wouldn't be an Airbnb presentation without one of our traditions. One of the things that we always do when we have like a presentation or we're talking in a group setting is we always talk about like a fun fact, something that kind of gets you to know the person that's either like presenting or talking in a group. So the fun fact I want to share with you guys today is that, so I turned 37 years old in about a month and a half, And I just realized I've been on-call rotations for almost half of my life. That's wild, right? So almost 18 and a half years of my entire life, I've been in on-call rotations. You must be wondering, like, you're 37, like, what were you doing on an on-call rotation when you were 18? So I'm actually a two-time college dropout. It's one of the reasons why I really thank you guys, because I've learned from all of you. School didn't teach me all this kind of stuff. I learned from everybody here. So I want to kind of take you on a little bit of a journey and talk about how I got here. So after the second time I dropped out of school, I was around 18 years old. My mom pulled open the newspaper. She was like, you need to get a job. She looked in the classified ads, right? This was like 1998. GlobalScape was the makers of QtFTP. How many of you guys remember QtFTP? Wow. Okay, so I probably supported you guys during my first 3 months there. And then after that, I became the webmaster. I was responsible for ensuring that the GlobalScape website was always up and available. I did a bunch of HTML stuff. I was really badass at tables. I could turn a PSD into tables really well. But it was interesting because we didn't have like an ops team. There was no SRE team. This wasn't even really kind of like a thing at that point. So they asked me, hey, would you actually carry this pager, right? Would you carry this pager and resolve issues as they came about? We didn't have a monitoring system. It was basically if somebody noticed that the site was down, either they would notice a support ticket come through saying that they couldn't download QtFTP, and then I would literally get a page on my pager for 911, meaning I had to go do something. I didn't have a cell phone, so I couldn't call somebody and say, what do I do next? I literally had to get in my car, drive to our office. That's where our NOC was. Right? We had like a little area in our office where all of our servers were, and I had to figure out what was going on, reboot it, and then hope everything came back up. You must think like, oh, you were 18 years old. You must have been out doing a lot of really fun things. Nope. Not a lot on the weekend. I lived about a half a mile from the office, and most of the time I had friends over. They'd bring their computers over. We'd have a LAN party, right? It was a lot of fun back then. I spent a lot of time mudding. That's how I originally learned how to code. And one time I actually fixed an issue, and I noticed the tech support phone was ringing, and a guy was having an issue downloading QtFTP. I helped him download QtFTP, and what a lot of you people might not know is you might think that it was mostly used for folks like us that were transferring files back and forth from servers, but it was actually mostly used by people that were sending files up to GeoCities to sell their listings on eBay. And this particular phone call that I picked up was a guy named Billy from Mississippi that had a belt buckle business selling on eBay. So after that, I actually got a job at Rackspace. I was there like in the very beginning doing managed hosting. I ran the Linux support teams there where we were basically the on-call team for all of our customers. They could call, within one ring someone would pick up, and the next thing you know, you could be compiling PHP for them, dealing with some kind of Apache issue, helping them with anything that was happening in their system. After that, I moved on to Sugar CRM, spent some time at Clout, and then spent some time at Flipboard. And lately, I just became an advisor for companies like Ship and RIFC, the makers of the GIF keyboard. Someone mentioned yesterday, or a couple days ago, that they had like a propensity for joining companies whose logos were blue. I seemingly have an issue, or I seemingly like to join companies whose logos are red. You might say Ship's logo is green, but I'm terribly colorblind, and I can tell a long story about how we had a serious outage at Sugar CRM for a long time because I couldn't tell the difference between an amber light and a red light on a switch. So thanks, Cisco. Which brings me to where I am today. I joined Airbnb about 10 months ago. I actually didn't make these slides. We have a really cool team back at the office that creates these amazing things that we can put into presentations. And I joined about 10 months ago at Airbnb and have been building out the SRE team there and figuring out how we do a lot of the stuff that the folks in this room do. So just to kind of talk about where we are in terms of scale and what we're supporting. In 2009, you can see this is a map of the world and all the listings that we have available on Airbnb. So in 2009, you can see we were heavily concentrated, just North America, a few hundred listings out there. And over time, you can kind of see our global scale in 2010, 2011, we're growing all over the world. And then finally, you can see where we're at the end of 2015. So at the end of 2015, we had about 2 million homes available on Airbnb for listings. 34,000 cities, 191 countries. So that's 2 million homes that depend on Airbnb to be up, to be able to be available for folks to be able to come and stay in their listings. And our mission as a company is to help people belong anywhere. We think that with our host community and staying with a host, you can best kind of experience a city or a town or an area and really feel like you're actually living there. So why is monitoring super important at Airbnb? So there's definitely like the online component. You know, you're searching through listings, you're finding where you want to stay, you find the listing that you want to stay at, and then you book it, right? That entire process has to be really solid, really available to be able to power those 2 million listings that we're looking at. But there's also a huge offline component to Airbnb. There's checking in with your host, right? There's all these details that come from like viewing your itinerary, messaging back and forth with your host. And if Airbnb is not available, there can be some serious problems there. So this is actually the listing that I'm staying at here in Portland. It's out in the Alphabet District. It's actually like a Marine Layer is a San Francisco store, clothing store, and I'm staying in the small little loft above that. So if I weren't able to view my itinerary, I might not know how to get into the front door. And if I'm not gonna get in the front door, it was really, really hot on Sunday. I didn't wanna be sitting outside baking. And let's imagine if I didn't know how to contact my host or message my host to let them know that like the water heater was broken. I might not be able to take a shower for a few days, right? And none even you would want to sit next to me. So how do we go about doing monitoring at Airbnb? We use a few commercial tools to be able to do this. We made a decision early on that we didn't really want to focus too much on building out our entire like own time series database, coming up with building a lot of custom dashboards. And a lot of the great tools that a lot of people were talking about weren't around when Airbnb was incepted. So one of the tools that we use is New Relic. So New Relic actually gives us a lot of stuff for free. Simply by including the New Relic gem into our Ruby applications and our JVM applications, we get a wealth of data about how that is actually working. So we can do deep introspection into the different timings down to the controller. It gives us tracebacks, it gives us error rates. We can look at the error rate after we do a deploy to ensure that everything is operating as it should after deploy. And then one of the other big tools that we use is Datadog. So Datadog is our primary like time series database for most of the metrics that we collect within the system. So we have the resident agent collector that's simply pulling down metrics from the system, like the typical stuff like CPU, memory. And then we also have instrumented the majority of the application using DogStatsD. And for those of you who aren't familiar with DogStatsD, it's very similar to Etsy's StatsD protocol, except that it has an augmentation of being able to add tagging on top of that to be able to drill down and filter on what we're looking at. And then we also use a bunch of integrations. We're 100% on AWS, so we're pulling down information from CloudWatch and bringing that all into Datadog. So one of the ways, the primary way that we do alerts at Airbnb is simply through metrics, right? We don't have a system like Nagios or Sensu that's doing like port health checks or pinging systems to ensure that they're live. Everything is based on either those instrumented metrics or metrics that are collected by the system. And we do alerts based on different thresholds or availability of those metrics. So Datadog actually gives you a great user interface to be able to create metrics. It's something it's hard to repeat, but you can go ahead and like select a metric, select the tags over the metrics, and then build out the alert through their UI. So at Airbnb, we're very focused on infrastructure as code, right? Like everything that we do within our entire infrastructure is code. So when you're looking at this, it's really hard to repeat, and it's really hard to kind of figure out the best way to define your metric. So we came up with an open source project that we call Interferon. So Interferon isn't specific to Datadog, but it's an open source tool where you can basically store your alerts configuration as code. It has, the main configuration for it has host sources. So these are the different things that you can query, like if you have some sort of like dictionary of all your services or dictionary of all your hosts, or some sort of like queryable data source that gives information about your environment. And for us, we use Optica, which is kind of like our representation of every server in our entire environment and all the metadata about that server that we pull in from both AWS, that we pull in from Chef, and stores all that information. Destinations, our primary destination is Datadog. So this integration was built with Datadog in mind. Groups, so these are how you define particular users and groups or integrations that you want to be able to send alerts to. And then obviously alerts. So these are the alerts that are kind of like the infrastructure as code, where you're looking at how the actual alerts define in Ruby. You can check out Interferon by going to Airbnb.io and looking at all of our other open source projects, or also going to the direct GitHub link. So let's take a look at a sample alert file from Interferon. So this is actually an alert that's based on our search availability. So if the P95 response time is greater than a particular threshold, it's going to fire. So these particular fields map up almost directly to the Datadog UI that I was showing earlier, but you can see that we do something a little bit unique in the message. So instead of creating runbooks for every single system where you have to look at the alert, understand which runbook to go to, maybe click through on that, we include the actual runbook in the alert. So the first thing, if this alert were to fire, you would go check out the search health dashboard on Datadog. You might want to look at the New Relic dashboard as well for search. And if the CPU load is spiked, you might want to deploy new machines, and there'll be a link directly there to go ahead and begin deploying new machines. And then also, if that's not quite working and you want to decrease the amount of like search QPS, we have a kill switch that you can throw on to be able to help reduce the load against our search environment. There's an applies construct where you can use some of the metadata from your dictionary service to be able to figure out which host this apply to. And you can see that this is actually looking at the chef role for search. So this would apply to any machine that matches the chef role of search. The notify groups, this is the group that I was talking about earlier in terms of which group should be notified if search is down. And then down here at the bottom, we have the metric, the Datadog query, and this is the actual representation of the metric in Datadog that we're alerting on, filtered down by the tag of the chef role search, and then with a threshold of what's previously defined. So to take a look at how those groups work, we have integration with PagerDuty, Slack, a bunch of other tools. If you were to use Interferon yourself, you could define your own integration. So for that particular search alert, this would obviously go to the Slack room for the search team, and then it would also go to the PagerDuty rotation for the search team as well. And then at the bottom here, we have like another integration where you can actually send this email. So one of the unique things about Airbnb in terms of on-call is that we don't do things like most teams. So we have individual product teams, they're on call for their own stuff. If you're building your own service, typically if you're building your own service behind our giant monorail, you're pretty much going to be on call for that particular service. But for kind of like general site availability and all of our like core business metrics that we alert on, we actually have a volunteer on call. So 11 months ago, before I was deciding to come to Airbnb, I had a long talk with Mike Curtis, who's our VP of engineering. And I was like, okay, you know, seems cool. I can come in there, do my SRE thing, sounds awesome, but like, how do you guys do on call? And he's like, oh, it's volunteer. And I was like, this is bullshit, right? And it's like, how did people volunteer for this? Like, isn't this like SRE's job? Like, isn't half of our time supposed to be spent like doing reactive things and making sure that the general availability of the site is great? He's like, no. He's like, yeah, SRE is going to be focused on making sure that everybody else can do on-call effectively, including like our volunteer organization. So how did this come to be? So we've never, before I was hired, we never really had an SRE or an ops team. Really early on in the day, we had one person that was on call for everything. And in an engineering meeting, our CTO basically asked, like, hey, does anybody else want to be on call? 4 other engineers rose their hands, and suddenly we had a volunteer on-call organization. And then after that, like there's been a few kind of like interesting things that this group has done. So there was actually like a gong in the office that someone would ring anytime that there was like a site availability problem or something was wrong. And then all the engineers that were part of the sysops team, they would go to this group of standing desks that they called Standyland and resolve on the issues. So folks would come back from lunch, or they'd come in early in the morning and they'd see folks standing around Standyland, and they're like, oh crap, the site's down, and they would ask them for updates. But it was kind of like a unique way of both visually representing, and not just through metrics, that something bad was happening on Airbnb. And then after that, obviously as the engineering organization began to scale and the amount of different services that we have and the complexity of the systems began to scale, it wasn't tenable for just 5 people to be on call. So the next thing we kind of figured out was, how do we get more people to volunteer? How do we get more people on this on-call rotation? And it was actually simpler than we thought. So one thing that we do every quarter or every 2 quarters, depending on how many people want to join the rotation, we actually have like a sysops training. So during boot camp, which is something that every engineer goes through for the first 3 weeks, we teach everybody in the entire company about how to use New Relic, how to use Datadog, how to use our Elk stack, basically all the different monitoring tools that we have, just so that everybody has that base for their particular teams. But sysops training, we go a little bit deeper. We learn how to remediate things. We learn how to be a good citizen on call, how to keep people, how to communicate with customer service, and how to effectively use PagerDuty. And we also have learning sessions where people learn historical incidents and learn about past ways things have broken, so they can kind of build up that compendium of knowledge for how things could potentially break here at Airbnb. The next thing that they do is there's a daily rotation that they get added to. So you'll have your primary and your secondary person on call, and then this daily rotation is someone that's new that's joined sysops will be in parallel with primary, so that as an alert comes through, they can see it, they can understand what's happening, they can jump in the Slack room for the incident, talk about it with the primary, or they could even go sit with them and learn how to do incident management hand in hand with somebody else. And then after that, we kind of throw them into the fire. You're promoted to being on call, and based on all the stuff that you've learned, we hope that you become an effective on-call incident manager. So one thing that we do every Friday afternoon, we have a weekly sysops meeting. It's actually held in one of our conference rooms. It's called Strangelove. It's based off of the war room from Dr. Strangelove, and this is an actual picture of the room. It's actually like pretty neat. So in this meeting, we have our sysops chair, who's not someone from SRE, not somebody from the infrastructure team. It's someone that's really exhibited what it means to be a great sysops, and it's actually one of our great engineers from our risk team right now. And one of the previous sysops chairs was actually somebody from our Android team. So one of the beautiful things about sysops is that you don't have to be on an infrastructure team. You don't even have to be on kind of like a back-end team. You can be anybody in the entire engineering organization, and it's our job to make sure that we can help you be effective. So in this sysops meeting, we go through kind of like all the incidents that happened within the previous week. We talk about metrics. We do a handoff to the next people that are coming on call, and we also we have the handoff to the people that are coming on call, and we discuss any maintenance that we're going to be doing in the future weeks, so that everybody's informed about all the things that are going on in the team. So one of the other fun things about sysops, even though we're a cross-functional team, we actually we act ourselves as a team, and we actually have offsites. So one thing that the team did last year before I joined, and I'm really upset that I missed this because I heard about it and I was like, this is the most amazing thing ever, is there's actually a ranch in Yorkville, California, where this team actually went to go yak shaving. So they didn't actually like bust out any shears and like shave yaks. It was more kind of like yak trimming. But one of our engineers called this rancher and was like, hey, do you have yaks? And can we come shave them? And they're like, sure. So it was a really great offsite. I've heard many amazing stories from that day. I'm sad that I missed it. And just so you know, there were no yaks that were harmed during this yak shaving offsite. Everything was very respectful. And we also do great things where we give everybody great hoodies. I was actually going to wear it up here today, but it's been really, really hot in Portland, and I didn't want to sweat any more than I already am. So, past, present, and future of SysOps. The initial incarnation of SysOps was all about remediation. It was folks that were actually fixing all of the problems. And our stack was simpler then, and it was really easy to kind of drill down on an issue and figure out what it was. These days, we've become more of like a triage unit. So alert will come in, and if you feel experienced enough to go ahead and solve that problem, you can go ahead and fix it. Otherwise, you're looking for the best person on another team to kind of figure out the root cause and figure out what's going wrong. And then health. One of the things that we're looking for in the future is that we have all these great people, well over 50 of them, that have volunteered to be on call. How is this affecting them? How is this affecting them in their daily jobs? So one thing that I've been casually working on since a little bit last year, I originally hoped to open source it here at Monitorama today, but priority shifted and I didn't have a chance to fully work on it. But I wanted to kind of show you guys kind of what I'm thinking about in terms of on-call health and how we're doing things. Katherine actually had a great presentation earlier today where she was talking about all the great stuff that they've done at Etsy, and I'm beginning to think about a lot of those same things. So on-call health, how are our weekly alerting trends going in the right direction? And do we really understand the impact on our on-call engineers? Are there any false positives that are constantly leaking out that we need to tune? And then are there teams that need better on-call training? And are the rotations and notifications for particular people appropriate? This originally started as a project to make sure that every rotation had an actual schedule associated to it, and not just not just one person that was constantly on call for a particular service, and also making sure that every engineer set up something other than just email, right? So you can set up PagerDuty with just email, but you actually need to have it either send a push notification or SMS you or call you to be effective. So it was kind of like our validation there. So I started building out a simple UI. I'm not a very great UI designer, but I'll take you through some of the screens. So looking at our weekly incident totals over the year, this shouldn't be going up, but we actually have more alerts being created every week that teams are working on that end up driving it up a little bit before it becomes tuned. We're measuring our mean time to acknowledge, our mean time to resolve, the count of the last week's weekly incidents, our weekly average, and then the year-to-date amount of total incidents. Next thing we can look at is the daily heat map. So for whatever reason, Tuesdays are a really bad day for us in terms of alerts. You would think that Mondays or Sundays or Mondays would be bad for us because going into the summer and through November, every Sunday is our biggest day ever, and then every Monday is our biggest day ever in terms of throughput. But somehow on Tuesdays is when we have most of our issues. And then we track incident counts by service, which teams are dealing with the most incidents. And then we look at total user notifications. I actually changed all the names on here because I didn't want to show anybody from Airbnb in particular here and how much they're getting alerted. But we track the total amount of alerts that they received over that week, and then how many came during non-business hours or nighttime, right? And this is actually a very, very important metric to really understand how much alerts are really affecting our on-call engineers. So you can see Jason, for that week, had 48 total alerts, 40 of them which were at night. And you can drill down a little bit further on that and see the heat map for Jason and what particular alerts and which particular nights were really bad for him. And then going back to false positive incident counts and noise candidates, these are alerts that resolve themselves within 5 minutes with no user interaction. Someone can acknowledge them, but if they automatically resolve, then that's probably something that we should look at. We should either tune it or make sure that it's not paging at all. And then incidents with escalation timeout. So this is for identifying areas where we need to improve our on-call training, where incidents are going through an entire rotation, an entire loop before someone actually responds. So one thing that I would actually love, we have one of our core values at Airbnb is being a host. It's all about what you do for everybody, what you do for other people, and what you do for the folks on your team. And most importantly, I think one of the big takeaways from me here at Monitorama is that it's really all about people. Right, a lot of the technology solutions out there can really augment our ability to do on-call and to understand our systems really well. But the most valuable asset every single company has here is its people. So making sure that they can do things effectively and they're not constantly interrupted and they can lead great lives is very, very important to the success of your company. So tracking things like sleep, some weeks can be really, really tough. And is it okay within your culture for someone to tap out, right? If after Tuesday on a week-long rotation, you haven't slept for 2 days, are there any signals within your tooling and your application to let your manager know automatically without you having to say something that you've had a tough time and that it should be someone else's turn to jump on call for that rest of that week? These are the kinds of things that I'm thinking about that I think we should all be thinking about in terms of measuring our on-call health. Just your general life. And this doesn't really apply to just people that are on call. Like we have a few engineers at Airbnb who are always around helping out with incidents. They might not be on call, but they feel kind of like obligated to be there and spend time helping others deal with incidents. And that kind of stuff should be tracked and measured so that we can have conversations with them to make sure that they don't feel obligated to have to continually do this, that everything will be okay if they happen to take a step away. So one of the things that we started looking at was building something that looks at our incidents channel in Slack and measures the amount of time that folks spend in there and the amount of time they spend in there in active conversations. And it's been a really good indicator for things that we need to look at to make sure that the people are spending time away from Slack and away from incidents and leading effective lives. And then recognition. Are you appropriately recognizing on-call work and work to eliminate tough on-calls, right? So if those false positives are constantly happening, or if there's a constant issue that's bringing down the system, are we not just simply dealing with it by throwing hours of it on it by being on call? Are we actually getting to the root cause and figuring out the best way to solve those problems, and are we rewarding that properly? So one of the going back to harmony and talking about that a little bit, I think that this is something that I would love to work on with many of the people in this room. I know a lot of people probably have thoughts about great ways to use a lot of the data that you can consume from the PagerDuty APIs to build effective tooling around how we think about health and how we think about on-call management. And if you'd love to talk to me about after this, I would love to talk to you. But I think if you feel like you've leveled up from being here in terms of like learning about your tooling and your knowledge around metrics and how to collect those things and how to build monitoring systems around that, I hope that everybody will go back to their respective companies and be a host and really think about the health of your employees and the health of the folks that are on call. Otherwise, I'm going to send the bear shark after you. So that's it. That's all I've got for today. Thank you guys for your time.
Hello, thanks for having me. I'm really excited to have the opportunity to speak here on a topic which is very core to my heart and my interest, namely statistics for engineers. Yay, statistics. Who loves statistics? Yeah, that's very nice to see. So before I dive into all the math things, I just want to say a few words about myself. My name is Heinrich. I live in Munich at the moment, and for people who are not familiar with Munich, it's a city in the EU, still in the EU, and I'm very happy to be a member of that great community, and I want to express my really sincere sadness about the UK, who has expressed their urge to leave it, and I've also spoken to a few folks here who are directly affected. It's really a sad event to see them leave. Apart from my national identity, I have also a cultural identity, which is I was a mathematician. I come from a town called Academia, and I am here a refugee in the monitoring community, and I want to thank you all for welcoming me here. And it has been a very warm welcome. And also, this particular place at the conference underlines this a lot. It's a very, very nice atmosphere, very interesting talks, and I can relate to many of the messages which were put out here. So, but remember, this sign, PhD, is actually the symbol for the refugees from Academia. Right. So, what I'm doing here. At the moment, I'm working for a company called Seconus. You might have heard of it. It's a monitoring analytics platform, and I'm the lead on the analytics part. So, statistics for engineers. I have been asked to talk about this in the last year a few times, and I actually did so, and I also put a lot of things to writing. Most notably, there has been a recent article of myself in the ACMQ, which is a great magazine, which is available online for free. So you can read that thing, and these slides will be on Twitter, so you will have the opportunity to find that article and also read about all the topics that will be covered here. I will use that shamelessly as an excuse to skip over topic and go fast. It's really, really tough to distill a lot of statistics and stuff like that to a 30-minute presentation. So please look at those blog posts and articles to learn more. There will be also a 3-hour version of that talk at SRECon in Dublin in a few weeks. So if you like, attend this. But of course, as long as I'm here, feel free to come to me and talk about it. And maybe I will have time for questions later in this presentation as well. Okay, so I've been told that mathematics can be a little bit dry from time to time. And to make it more engaging, you should always put it into a story and make it personal. So what I want to do is I want to tell you a tale of API monitoring, like a problem that many of you will be able to relate to, and in the very concrete form of a fictional web store, which I call Attic. It has a great API, which is just a web interface it exposes. It has a catalog, which the users can see. And it has this funny thing that they lose money if requests take too long because users get offended. And they want to monitor this API. And I will tell you through the tale how they started, what they tried, and what kind of mathematical difficulties they ran into and what you need to know in order to make sense of your data. So what do they want to do? The main goals of monitoring are to measure the user experience and the quality of your service. Is the service up in the very, very least, but also how do your users feel about the service? And you can, with good monitoring, you're able to determine financial implications of service degradations, and you can then take these metrics to define sensible service level targets for your dev and ops teams. As I said, I'm coming from the mathematical side, but I feel that it's not, failures happen, and it's really about defining sensible measures of how much error is okay and how much at the end, often financial implications are suffered from the errors that happen. And to give you a basis for your discussion, that's one goal, a key goal of monitoring APIs in particular. Okay, so the very first step, if you approach the problem of monitoring a website or an API in general, is a theme of external monitoring. So what you might do is configure a synthetic check that reaches out to your API once every minute and looks if this request is successful, if it was an error, and you might measure the latency of that request. So if you do that with our tool or other monitoring tools, you arrive at charts that look like this. This kind of charts are great if you want to measure pure availability, so is the service actually reachable, and you can use it to alert on outages. It's bad, however, to measure any kind of user experience. Remember, you just have a synthetic request, so the only thing you learn from that how you basically serve the robot. So there's not a single user involved with that request, and there's also more doubt or more problems with this kind of monitoring in that these request patterns are often very easy to cache or to predict. So with high probability, this one request you're making, maybe to your home site, will be served completely out of cache, and the only thing you're measuring there is the performance of your network. So this kind of graphs are actually very often seen. So you have this kind of spikes, and otherwise like a measure here. There's another thing which I want to point out here is that, of course, this kind of graphics are always produced with Synchronous. I will make no excuse for that. But one thing, we use this kind of bar-like things, which I like, in compared to these line charts we have seen a lot. The one point here is that the line charts always suggest a kind of continuity between that. So if you've gone from this point here to that point here, these are just two measurements. At that minute, you had that duration. At that minute, you had that duration. There's absolutely no sense of continuity between those two measurements. And I really have to just move my mouse every other minute. And that's a little bit of a misleading visualization. So if you are looking at line plots, always ask yourself, is it really justified to draw a line which has this sense of continuity, or is it not like better served by kind of these dots or scatter plots or other kinds of visualizations which show you the true data? You don't want to be misled by your visualizations, you want to see the actual data points. And there's a problem which is way, way more severe than just the drawing of lines. That's actually the phenomenon called spike erosion. So this is the same graph on a much larger scale. So you see like April to May. So this is actually like good months, a little more than a month. There are, I don't know, very, very many measurements which were taken in this whole month. So you have to calculate the number of minutes that were in this month, which is a huge number. Or a big number. It's certainly more than the actual amount of pixels you have available on that screen. That means every time you look at graphs which have more than like an hour or this kind of small time periods, you will see aggregation all over the place. And what I did here is I used what we call a histogram aggregation or a min and max aggregation to make you aware of how drastic the effects of aggregation are to your data. So what you see here is the usual view that many tools will present you. What you will see here is how the same graph goes on. And in addition, I have drawn the actual measurements as a kind of heat map. So it looks a little bit like dirt. We call it actually a heat map or a histogram. But the essence is these are your actual measurements. There are very, very little points sprinkled all over this map. You see you have a lot of measurements up here. So this other line is the actual one-day maximum latency you have been experienced. And the points down here are like other measurements. And for each of those values in the line graph actually represents I think a 1 hour average of all measurements that are made. So you're actually seeing a compressed information of 60 data points. And that's a drastic thing. So our clients tell us we can't do capacity planning on averages. So if you look at graphs like request rates, you don't have any idea of your maximal latency if you're looking at a chart which is aggregated in averages. The actual data distribution will be all over the place. And there are certain metrics which are okay to be averaged, like disk utilization, stuff like that. But for many things, especially the volatile metrics, it's very, very misleading if you look at those slides at a large time scale. And it's a problem that like many tools have, and it's not so easy to address. They're actually, like, you cannot blame the vendors or the tools, because shipping you all the data points might involve sending 50 megabytes of JSON to your browser and then crashing your browser because your rendering engine can't do it. So that might not be a smart choice either. Sometimes it's just better to get a rough idea. But keep in mind, if you're viewing timescales of weeks, you're just seeing a very, very thin shadow of your actual data. So part two. So after they have done external monitoring, which is a great thing to do, they said, well, okay, how can we do better? We need to understand our API more. We need to serve actual users. We need to measure actual users. We cannot only measure robots. So they started log analysis, and log analysis is also a very great thing. So what you do is actually here you write to a log file the time of completion of your request, or the time where the request went in, the duration, the request latency, and all kinds of further metadata you have attached to that. Maybe the document retrieving, maybe a session ID or whatever. It's a very, very rich source of information. It's pretty trivial to do instrumentation with log files, just printf. That's very, very cool. And you can compress very, very high dimensional data into log files. So you cannot compress it, but you can store it. You have a lot of rich information about the requests. And here's my little attempt to draw the kind of numerical information you get out of there. This is the UML version of the API, the internal API. So you have a user making a request at a certain time. There's a request latency, and there is the response send out. And all this information is contained in your log line. So every of these blue lines would be a user making a request, coming back. It's the information, the numerical information contained in a log line, which is great. It's the actual users you're measuring. It's like the best kind of information you can have about the API. The problem here is, and it's common to all log tools, it takes very long to retrieve the data again and to store it actually, because the format is so inefficient. It's inefficient as in big data. It's one of the really single ways, or the rare ways, how you can actually produce petabytes of data. And if you're just looking at 1 year or 1 week, you have to digest all the log files. So it will be slow, and there's no way around that. And for that reason, also expensive. And if you do very, very high latency APIs, high volume APIs. So I put the example of a web store first, but APIs are everywhere. This is a very, very universal topic. I mean, you all know about services and stuff like that, so microservices, but also your layers in your software architecture, like syscalls. Syscalls are an API, block devices are an API. APIs are everywhere, and you might want to also capture latency information, capture performance information, all of those kinds of APIs. And imagine doing syscall latencies with log files. This is not going to work well. However, it's great if you can afford it. So if your API is low volume enough, then by all means do this kind of logs, write out the excesses as log files. So here on this slide, I have tried to digest the numerical information you get out of the logs and the API usage in a more concise way. And give you another mental model of how to reason about your API. So in the next slide, I have the construction of that. So it is very easy. So if you have this UML version and you're all with me, what this diagram here means. So what I want to do here, or what I've done here, is to use a second dimension and put it to use for us. So instead of showing the latency as a here time stretch, I will rotate the latency and put it on the y-axis. So every request will now be represented by this kind of vertical lines, yeah, that's correct. And the height will say how long the request took. And here's another little bit about math and this kind of subtleties of monitoring that I want to point out. You have two choices here. You can rotate the thing on the left or the right. You can base it on the time the request went in or the time the request went out. The problem is, if you are right here at this point in time and have a request in flight, there's no way, I do not know how long this request will have taken. And if I want to give you the full information, if I want to put that slide on the other edge and base that thing here, I have no way to produce that graph at this very point in time. And these are, I don't know if I expressed that really clear, but there's a trade-off between timeliness of your data and correctness of your data. With putting the chart on the start time, I have no way to produce correct data. Only by putting it on the request finish time, I have the full data available that I want to plot at a certain point in time. So here is another visualization of your API. And by that, if I now have my math hat on, then I will say, well, great, I have so many tools how I can analyze this kind of patterns, this kind of data I have available from the API. So I might project the data to the y-axis and put a histogram here. So this is for what we call a marginal distribution, and I will have a probability density function and a maximum likelihood estimator of certain probability distributions. So, and all kinds of statistics I can do with this kind of boundary distribution. As a mathematician, I see a kind of a arrival rate process, and I can mumble Poisson distribution and just attack it from this angle. And if I'm really fancy, I can remind myself that a request is not on CPU all the time or served all the time on CPU or on like just the machine doing work. It might actually be in a queue for a little while. And there are fascinating problems about like balancing concurrencies and request rates and determining capacity, which are which you can analyze from the angle of queuing theory. And there's a great book by Baron Schwartz about queuing theory, which I want to advertise here. It's really a great read, and it's yet another mathematical angle you can have on that. If you're talking to your sales and your marketing team, you will, however, have a pretty other view on this API. Because they will not say this is a percentile or mean value. These requests are actual people doing the requests. So, and depending on how you serve the request, they will be more or less happy. So some people will be served, they will be super happy. The Google bot got served, it's okay, it isn't happy or not, it just indexes your site. On this guy, you actually just pissed off really hard. He's leaving, going to the other website, or he's going to Google again and then take its business everywhere else. So requests are people, those latency actually matter, and just putting percentiles on it and mean values on it often hide the fact that you're actually talking about people, their emotions like hatred if their requests take too long, or money if they go somewhere else, right? So you really should care about this kind of things. Okay. So what can you do, what can you do next? So what many people do with these kind of things, they need to find a way to compress the information in the log files because they're just too large. And what do? They take the mean value. And here we come to a topic of my core expertise, calculating mean values. That's always fun. So what you do is you actually sum up all the values here and you divide by the number of samples you received. And if you want to have a physical analogy of that is if you have a lever, I think that's the right word, it's like basically a kind of thing that shakes to both sides, and if you put equal mass on all of those things, then this will be the equilibrium supporting point. So this is the physical explanation of a mean value, and what the physical explanation actually will show you pretty easily is that if there's one point on this lever which is way outside, it will skew your whole distribution to the one side. So it's very easy to affect mean values to the top, and it's also very easy to change mean values to the lower end. This is, again, a problem with caching. If your static store is measuring all requests, many of them will be cached, and you will have very low latencies, and the mean value will not be a very useful thing. So, for example, here's how that might look like in one of the examples that we have. Here you have outliers all the time, and here crazy things happen on the boundaries. I might ask you what it actually happens, but it takes too much time, so I will just say it. There's actually nobody on the side. It's night, and there's 4 requests, and it's Google indexing your site, and they have really bad cache hit ratios, so the mean values are way off. And this is how that looks. Right. So what you have to do for this request latency monitoring is you have to first select the reporting period, and I didn't really spend a lot of time talking about that, but it's also a very essential step. Then you can calculate the mean value, and there you will have, if you have measured actual people, it's very steep to collect, store, and analyze, but you have skewed your distribution, or you have compressed an awful lot of information into one single value, and this is always a very problematic thing to do. And I was asked, how much time do I have left to present? Nobody knows. Maybe 15 minutes? Okay. Right. So this is some ways how to do better. There are ways to address like the outlier problem by, for example, taking median values instead of mean values. You can actually go a little bit fancier with truncated means, idea being you just throw away minima and maxima and then take the mean value from there. And you can also try to collect deviation measures, but this is also a very delicate topic. Okay, here's the next idea. So people are very aware that, averages are a problem, so what they turn to next is percentiles. What is a percentile? Just really quick, the basic idea of a 50 percentile is it's a value that divides your data set in a half, bottom half and the top half. The idea of a 99th percentile is you divide your data set into a top half and a bottom half of 1% and 99%. A little thing about percentiles that not many people know is they are actually not unique. So for example, the 90th percentile, every value in here between this whole two things qualifies in the 90th percentile. So be a little careful with the actual definition. If you look at Wikipedia, there are 8 different ways to make percentiles unique. You never really know which one is the right one for you. And I'm going a little bit fast here, but I want to come to also to later slides. How the percentile monitoring method works is first you have to select this reporting period, which tells you how much values you're actually putting in a bucket. Then the second thing you do is actually to compute this latency percentiles, you can just sort the data and you will have a really quick way to compute the percentiles by just then counting which nth of this values you need. And then you calculate for each reporting period, again, this choice is really essential, like how much time and how many values you put into this percentile. You calculate the 50th, 90th, 99th percentile, you store that as a time series, and then you alert when percentiles go over a certain threshold value. And this is actually not a bad mean at all to judge your API, user happiness or your API performance. You measure the actual requests. You have a way to do so without collecting massive amounts of data. It's robust to outliers, so the single spikes we're seeing are going away. The 2 drawbacks are you need upfront choice of those percentiles, and it's not always easy to tell which ones are precisely the right ones for you. And then the very last point is percentiles cannot be aggregated. And I will come to that point again. So here how it looks in practice. Here's the 50th percentile, so this is what directly competes with this guy here, mean value on median, and you see median is a little bit nicer. You see this 90th percentile down here might be a good way to alert on, like 90% of your users were happy or reasonably happy, and the 90th percentile, you know, okay, with very few users, I have actually just not done a terribly good job of serving them. But it's, yeah, you have also these terrible problems at night, and it's just also a little bit not very intuitive what the message is if you look at a graph like that. Right. So, and now I want to make that very last point on the slide again, which is percentiles cannot be aggregated. This is a very severe problem with percentiles. The median of two median values is not the median of the total sample set. If you have two nodes and compute the median, which are serving the same API, and you're computing a median on that node and a median on that node, you will have no way to know the total median. If you are computing a percentile over a 1 minute period and over another 1 minute period and in total 5 1-minute periods, you have no way to calculate the percentile of the 5-minute period there. So with percentiles, to do percentiles correctly, you have to know which kind of aggregation levels, which kind of aggregation periods, and which percentiles you need. You need to know all this information upfront, and you need to collect all of them and never ever roll them up. Because the average of percentiles is just completely meaningless value. It's like, it doesn't tell you anything. It tells you some ratio was here and another one was there, and you will have no idea what it actually means. So it might be okay to get a rough idea of your actual data, but keep in mind how misleading averages can be. But try to keep your percentiles non-aggregated. Store them all, so you will have meaningful values. And again, I mean, if you are tuning some SLAs, you never know which kind of percentiles are the right ones to look at. Do I do 99.9, can I serve 99.9% of my users well, or more or less than that? So if you do all of that, then percentiles come and with a significant cost. And we have also written about that on our blog. Okay, great, just 2 minutes. That's good to have the half of your presentations compressed into. So what, yeah, it just happens. Okay, so how can you do better? And let me go give you a little survey. So what we propose as a solution to that problem is actually histograms. And this is what many people use internally on their agents to compute these percentiles. So what you can do is take this request latency distribution and chop into latency bands. And for this latency bands, you just count how many samples there are. And here we'll have the familiar picture of a histogram. And it turns out you can actually store histograms. And you can do calculations with them. And you can store them extremely compactly. Compared to logs, this kind of histogram information is pretty compact. And it can be trivially aggregated across time. So if you have 5 histograms across 5 minutes, just add the counts. If you have 5 nodes, just add the histograms. So by storing histograms, you have the ability to do all kinds of slicing and dicing with your data, plus you can still derive all the relevant measures for you. You can derive all kinds of percentiles, you can derive averages and all kind of that with a little bit of reduced precision. This is the price you pay. Right. And you can actually visualize your API performance or your API usage. This is a histogram heat map representation of the API actually served by many nodes. This is search metric histogram, so it aggregates data from all nodes serving the web API across a period of 10 minutes, and it shows me this data as a heat map. So, and what you can see here, we have one line down here, that's the cached responses, and then you have like kind of lines going down up here. These are, there's actually a problem here. You spot it, the request gets slower with time. So you have a bug in your web service which causes this. And I would argue that it's more intuitive if you look at the heat map. You can still derive all kinds of other measures from it. So you can do the mean, you can do the percentiles, you can do the rate, like count how many samples are in the histogram. And you can do actually better than that. So this is the line that's, the number is arbitrary, but say this is 5 seconds. This is the moment where your users really get pissed off if you're serving them lower than that. This is where they're at their phone and they're saying, go faster. You can just count the number of users you have pissed off. And this will be a very meaningful metric for you. So this is kind of the quest, and I think one of the things we should strive for as a monitoring community, to search for more meaningful metrics which are directly meaningful to you, which directly measure implications to your business. And like in this example, you directly see the 90th percentile was not so bad for that, or the 90th percentile, right? It was not worse than there so much, but actually the volume you were serving here was much higher than it was when you were serving here. So the financial implications of that 99th percentile being over a certain threshold value was much higher than it was down here. So you really need to correlate the volume you're serving with the quality of your service in order to derive actionable information that is interesting to your boss. So that's one thing. And the other thing you can do, you can just count the total users you offended. That's also pretty awesome. So at the end of your day, you know, like 4,000 people are actually mad at you right now. So that was fun to know. Great. So I will close with this. A few takeaways on this slide. Keep your data, strive for meaningful metrics, and thank you very much.
Great, good stuff. Hi, I'm Daniel from Chef Software. I'm a solutions architect based here in PDX. And first off, I'd like to thank the Monitorama team for just doing a great job at this conference. I'd like to give them a hand. Now, I hope many of you are familiar with Chef, and ideally, we've been able to make IT automation more delightful for you. But today, I wanted to tell you about our new open source project we just released called Habitat. This is a bit of an eye chart, lots to take in, but don't worry, we'll persevere and unpack it. So Habitat is a new approach to automation that focuses on the application instead of the infrastructure it runs on. So today, many of us work from the infrastructure bottom up, but with Habitat, we're looking at things from the application perspective, which is top down. So most of us here either build apps or help run applications in production, and the current experience is captured on the left 2 columns of the diagram here. Now, developers today write awesome applications for the business, but to put it into production, one of the first things needed is a proper OS for the app. So looking at the bottom left column, we also need to consider the runtime configuration followed with the app on top. But that's not enough. How do we deploy the app? Or if we have updates for the app, how do we get them out there? So there's another layer here in the middle of our column titled management. And today, management tools could be Chef or other config management options out there. So that's cool. We figured out how to upgrade the thing and manage it. But when we deploy the app, is it alive? How do we health check it? That's where the monitoring the app service comes in, and you can use something like Nagios. Now, you'll have to figure out orchestration as well, though, making sure one service is up before the next, and only when they're all available can the complete service come online. So you'll see tools like CloudFormation, Terraform appear. And once your app is running, it needs to find a database, and so service discovery comes into gear here in the form of console, etcd, even hard-coded values. So that's not ideal, obviously. Now, if you look at the diagram, you see here there are, 7, 8 things you have to be good at to ultimately run the app. And so containers come along and say, hey, we're going to help you by making these releases more immutable. The container model provides the box in red where the runtime and application go. which becomes your releasable artifact. Except you still have to figure out how many containers are out there, how to upgrade them, so you still have the management layer problem, the orchestration problem, and service discovery. So all of us have to solve for this today, getting all of these things on a box in the right order, configured correctly. So what we're saying is this all adds up to complex sort of bottom-up model. But our application developer doesn't want to do all those things, they want to focus on the app. So what if we give our developers and ops people a framework where everything the application needs is part of the artifact? And that's what Habitat is about. It's a packaging format that contains the application along with the required runtime components, as well as the capacity to do other things such as service discovery, orchestration, monitoring, etc. The way it works is, as you run your Habitat package, there's a Habitat supervisor process that uses the gossip protocol to talk to others of its kind. They form a P2P network, we call that a ring, so that they can communicate with each other. So it's easier for you to find out how many of those things are out there. Easy for you to introduce a new release because the supervisor has the capacity to update the package. And it's also easy to do service discovery, such as ask where the database is, because these things are talking to each other. If you're running a topology where your services need to be in a master-follower config, the supervisor allows for that as well. So if you have a 5-node cluster with 1 master and 4 followers, and the master dies, followers talk to each other, hold an election, determine who the new master is. So with Habitat, we've solved for complexities that we all have had to deal with. That's because as part of the build process, you can produce a Habitat artifact that contains everything that you need. That artifact can now run on my dev workstation, on the test environment, within my Docker containers, on my production paths, deployed to Mesosphere or Kubernetes, VM guest, anywhere with just enough OS. So that is a lot to take in. I definitely appreciate that. So to learn more, you can get started and try all of this for yourself with the URL you see here. See if the experience is right for you. Check out the documentation and tutorials, and you can get it in your hands and just start to kick the tires on it. And lastly, we have our conference coming up in about a week and a half as well. I'm really hoping to see some or lots of you there as well. It's in very balmy Austin in about, 2 weeks or so. So lots of barbecue and fantastic community events coming up. And that's all I had. Thanks so much for your time. I appreciate it.
I'm very excited to be here today to talk about Monarch, Google's globally distributed monitoring system. It's been a real treat to be here and listen to all the stories about monitoring, and I hope this will be interesting to you. My role is I'm the tech lead for the query engine in Monarch. Monarch was built by a large team of dedicated and smart people who originally built it, keep it running, and have continued to evolve it. So I'm just the guy who gets to come here and talk about it. So let's start with a little background. Google obviously has a global monitoring problem. We have stuff everywhere, we have to keep track of it, but it isn't just global, it's huge volume of stuff. We're monitoring hundreds of millions of individual instances, targets across our systems. We're taking tens of billions of measurements across those targets. We're ingesting tens of gigabytes a second of data about them. It's a huge monitoring effort. There are many kinds of things that we're monitoring, a large variety. We've got obviously hardware, networking, operating systems, infrastructure services. We've got big user-facing services, back-ends and front-ends, smaller services. And there are many, many teams doing this. And those teams have responsibility for monitoring their projects. Google has a very strong culture of measuring things. You do not run things in production if you do not understand and can see and have visibility into how they're working. So monitoring is a big deal for all of those teams, and providing solutions for them to discharge those responsibilities is very important. And finally, obviously, it's always changing. It's constantly changing. So that's kind of the problem we're dealing with. Before there was Monarch, there was Borgmon, and that is how we solved this problem. And you could think of Borgmon as the rough draft for Prometheus, which you heard about earlier today. Basically, each group that had responsibility for monitoring its stuff had to set up its own Borgmon monitoring instances, configure them, deal with the problem of distributed monitoring if they had a wide geographic distribution, which usually they do. And the configuration was not a straightforward thing to do. It was difficult to learn how to do it and get it up and running. So there's a large barrier to teams discharging their monitoring requirements. They could do it, but it wasn't easy. And it was a large load. On small teams, it was hard for them to keep someone there who actually knew how to do it. There's kind of this joke about a hazing ritual. The new guy on the team is going to have to learn how to do Borgmon so he can do the maintenance on our monitoring configuration. And on large teams, it was just a continual difficulty to deal with the complexities of monitoring, setting up a monitoring system to monitor a very large and complex system. So what did we want? We wanted to set up, first we wanted a service for two reasons. One, to unload that kind of load of setting up your own monitoring system to monitor your service, but also because your service doesn't operate in a vacuum. It depends on other services. And what we wanted in terms of a monitoring service was the ability for you also to see the monitoring data for the systems that you depended on. And that's an important part of having kind of a unified service that everyone is using. Obviously, we wanted the service to be able to handle the scale of Google, and we wanted people to be able to get up and running quickly with a much shallower learning curve to get monitoring running and going for their service. But it also had to be powerful and flexible enough to handle the largest services, very complex services distributed over all of Google. So that's what we were looking for. So we have a global monitoring problem, and we want a service to solve this. Where do we start? Well, we start by monitoring locally. And we do this because most of the data that you collect is only looked at in aggregate. We aggregate it to decide if our system is healthy, what's going on in it, and we only look at the individual data things when we've identified some outlier and something that we need to look at. So what we do is we collect and store the data near where it's generated, and when we query, we aggregate and select near there to do that. So we start by monitoring locally. Well, how do we do that? We basically divide Google up into a number of zones. Each zone is a strongly connected network area, and we build a monitoring solution in that zone, a semi-autonomous monitoring solution. It's autonomous in the sense that even if the zone becomes disconnected from the rest of Google, it can continue to monitor the stuff that's in that zone. But semi-autonomous in the sense that it is integrated into a whole monitoring system that gives you a global view of Google and the systems that you're monitoring, no matter where they are in Google. So local autonomy, but integration. So what goes on inside a zone? Well, the monitoring starts with ingestion. And for Monarch, ingestion starts with the StreamZ library. So StreamZ is a library that is available basically on every piece of software that is running in Google's production. And it has two purposes, or two things that it does. One, it provides classes for defining metrics, which are measurements we'll take on the system. We'll see in a minute what that is. And the second is that it is responsible for communicating with Monarch and pushing information to Monarch. So what are these metrics? Well, a metric is a structured, potentially multidimensional measurement of some aspect of the target. So here's an example of one. A metric has a name. This one is measuring response latencies for HTTP server. It gives the type, the value type which the measurement is represented in this case, distributions. And I'll thank Heinrich for giving a very impassioned cell for using histograms, which is what is contained in a distribution along with a statistical summary, computing with histograms, because that's what this is. And this is multidimensional data in that we're categorizing it by the HTTP path that was referenced and the status code that was returned for a particular reference. So when a reference is done, you have the path that was on, the status code, and a latency, how long it took. And you give that to the StreamZ library. It finds the right element in this in the set of values for the metric for that request endpoint and status code, and adds the histogram value to, adds the latency to the histogram value. So this is a cumulative metric. In other words, the StreamZ is maintaining these counters and it's accumulating values. So the population of values that are characterized by the histogram continues to increase. So one thing to notice about this is that the first level of temporal aggregation is being done right on the target before we send anything to Monarch. And so the StreamZ library is maintaining these metrics based on being told, here's a latency, here's a latency, here's a latency from the actual application. And then it's also responsible for sending these to Monarch. Now, besides sending the metrics, StreamZ library is also sending a bunch of labels that basically describe what target this data is coming from. And these get organized by target schemas, which basically describe the kind of thing it is and which particular instance it is. So a very common one is Borg task, which is a task running on the Borg cluster management system. And it's characterized, it's identified by the user running the job, the name the user gave that job, which Borg cell it's running in, and then a task number that distinguishes it from all the other tasks in that job running in that cell. And so this is the way that basically we come up with a name, a structured name, for a particular target. Okay, so StreamZ is basically doing all of that, and it contacts Monarch and talks to ingestion servers. And it's basically going to push the labels that describe the target it's part of and the descriptions of the metrics that it has, and it's going to then send timestamped sampled values for all of the values that are kept in the individual metrics with the dimension labels attached to them. And the ingestion router is going to do a number of things. It's going to make sure that the Monarch system has a record of the metric description. It's going to it's the one that basically takes the labels about the target that are sent from StreamZ and turns it into selects a target schema to organize it and gets a name for it. It decides where the data for that target should be sent. And it also gives feedback to the target as to how frequently it wants the various metrics from that target to be sampled and sent to it. And that's something that is configured within Monarch in a way that we'll see, and gets fed back to the actual StreamZ library and the target to affect how frequently we're sampling things. So the ingestion router is sending stuff to the place where it should go, and that is a leaf. A leaf is the kind of center of the monitoring in the zone, a Monarch in one zone. And it has two roles. One, it contains an in-memory database of the stuff that's been pushed to it, and it is the lowest level of the query evaluation hierarchy. And the leaves are range sharded on the target schema name that's attached to the target. And so the ingestion routers keep a map that tell it basically what ranges are assigned to what leaves, and so they know where to send all of the metrics that come in for a particular target when that target is sampled. The leaf incorporates that data into its in-memory time series database, writes it out to a recovery log, and that recovery log is obviously the way that you recover during a leaf failure. It's also the way that ranges are moved from one leaf to another when you have to do load balancing for the RAID sharding. And the recovery logs are also the path to the long-term disk repository that has a longer horizon than the in-memory database in the leaves. Well, what are the leaves accumulating things into? Basically, they're creating streams. And a stream is basically a named time series. And the name is made up of the target that the data came from and the metric, the particular metric that is being measured on that target, not only the metric name, but the metric dimension labels. And so this identifies a particular measurement. Each time a sample for that target and a slice of the metric comes in, it comes with a sample timestamp, and it's added to the time series history of the stream with the timestamp and the value. Okay, so we're basically getting a time series of distributions being accumulated here for this particular metric. Now these streams can be thought of as being organized into tables, and for queries, this is kind of the organization you think of. And a table is something that's identified by by the kind of target schema being used, in this case Borg task, and the name of the metric. And that defines a set, in this case a set of 6 columns that identify in the database. And then, so each row in this is one stream, and the final column is the time series, the history that's in that stream. So this makes up a kind of relational model that is the basis for the queries. Okay, so queries. Well, queries come in from outside the monitoring, the Monarch zone machinery, and they're handled by a zone mixer, which analyzes the query, decides which leaves should participate in the query, and sends the query to those leaves. Those leaves query the in-memory database and also the repository, integrate the data, do some processing on it, send it back to the zone mixer, more processing, and then that goes back to whoever made the query. The query is typically coming from global Monarch, in a way we'll see in a second, but it could also be coming locally. It could be coming from something else. And we'll go into more detail on what queries, how queries are actually executed. The other thing that could go on in a zone is autonomous evaluation. It can be, Monarch can be configured to evaluate queries on its own in the zone. Those get set to zone mixers in exactly the same way. The query is executed the same way as an externally query, except we don't use the repository for those. And then there are two things that could happen to that. One, it could be written back to the leaf, so it gets ingested into, the query computes a new value for a set of streams, and it gets ingested into the leaf in the same way as if it had come from a target. And the other thing is the query can lead to an alert, some kind of notification, and that gets sent to the Google Alert Manager, which is another component that I won't be talking about today, but also has like zonal presence everywhere. So queries that can be evaluated in the zone can get sent to the local alert manager. Okay, so there we have it, something that operates locally in a zone. It's kind of a query system in a zone. But we have this global problem. What happens now? Well, we integrate this globally. Basically, we have a layer called Global Monarch that is logically centralized but physically distributed. So it's distributed for robustness, and it's distributed to maintain the autonomy of the various Monarch zones. But it's central in the sense that the user has one place to configure Monarch, one place to send queries to see all of Google. So that it is, in fact, a unified service. So the kinds of things you could do from Global Monarch are to configure Monarch and to issue queries that apply to all of Google. So configuration. The configuration basically controls the ingestion and retention of data. So I mentioned that the ingestion servers give feedback to the StreamZ library as to how frequently to sample things. That comes from a configuration that someone will have put into the configuration server, how long it's kept in the leaves, how long it's kept in the on-disk memory. It is through the configuration server that ongoing queries that are periodically evaluated are set up. The configuration server is also keeping track of all of the metric definitions that have been collected. It is a distributed Paxos database, and so in that sense it's logically centralized. It's one unified database, but distributed. And it has a huge amount of read replication, including in all the zones. And also the elements in the zones that use configuration information tend to keep local copies of that configuration information. So it integrates the zones into a unified whole, but the zones can still run autonomously even if the configuration server, the global Monarch, becomes inaccessible to it or is unavailable for some reason. All right, so that's configuration. Queries, the same story here as in the individual zones. The query comes in to Global Monarch, and there are root mixers all over the world. So if you're in Europe, you're likely to talk to a root mixer there. If you're here, you'll talk to one nearby. And those basically do the same thing for the zones as the zone mixers did for the leaves. So it's a hierarchical evaluation of queries. We'll see a little bit more of that in a second. And then you also have an evaluator here. So queries can be evaluated at the global level, and they can be sent to leaves to be stored, or can do alerts and notifications at the global level. And we'll talk in a second about how you decide where that happens, whether you do it here or in the zones. Okay, so we've got integrated Monarch now. We've got Global Monarch that is basically providing an integration of all of the semi-autonomous Monarch zones so that it appears you have a unified system that will show you everything that's going on in Google, but the parts of that system are still able to continue to operate relatively independently of one another. Okay, so one of the interesting things that shows how this all fits together is a little bit more detail on how queries are done. So we'll talk for a moment about queries. Here's a query. We have a notation for doing queries that's based on a kind of piping metaphor like Unix, where you basically, each stage is creating a table that flows into the next stage, which does some modification, and the table flows to the next stage. So you start here by naming a table, and that's exactly the table I had talked about in an earlier slide. You can give a filter that says what part of the table I'm interested in this case, jobs that are being run by Gmail. And then I'm going to aggregate, this query is going to aggregate the streams in that table by basically throwing away all of the stream ID columns in the table except for job and cell. So we're going to get an aggregated distribution latency distribution for each job being run by Gmail and each cell it's being run in. And then we're going to extract the 95th percentile from that distribution. I thank Heinrich for giving a very impassioned defense of this way of collecting and computing on data where you want to get percentiles. There are other things you can do in queries. Joins are very important to allow you to do ratios and compare things. Pick top stream is very important in terms of selecting out outliers. The expressions and aggregation functions can be very general. It can be given very concisely, which is very nice for doing ad hoc queries. You tend to get this kind of write-only query, which you can really understand as you're typing it in, but you want to use the more expanded version probably for doing configuration and that sort of thing. So here's a query. Let's look at how it might get evaluated. So we have our hierarchy, the root mixer, zone mixer, leaves, repo, the lower part of that being reproduced in all of the different zones. And the query comes into the root mixer, and it basically analyzes the query into its parts. So it's going to do the fetch, and the filtering is going to be one step in it. It's going to do an alignment step, which wasn't explicitly mentioned in the query, but in order to aggregate multiple streams, the timestamps in the streams need to line up. You need to have the same period and phase in all of the streams. And for cumulative streams of the sort that we're looking at here, the alignment stage also chops it up into chunks. So if you had a 1 minute period, it'll chop it up into chunks that correspond to the population of latencies that occurred in that 1 minute period, as opposed to the population of latencies, the cumulative population from when the server started. So that happens in the align step. Then the aggregate step takes a bunch of time series and time by time adds the distributions together. So you take two distributions with disjoint populations of values, add them together to get a distribution for the union of those populations. And that's basically what is aggregating going on. And then finally, once you've aggregated that, you're going to extract the percentile estimate from the histogram in the distribution. I have 1 minute? Oh boy, ha! All right. So basically, the query gets moved down through the various stages. Each stage decides what to pass on to the next and what part it's going to execute. In this particular case, we're seeing that the zone mixer is going to, the zone mixer is going to do aggregation and percentile. The leaf is going to do the fetching. That's where the fetching goes on. It may fetch from the repo as well. It will do the align step on each stream as it's fetched. Then it will aggregate those. It can't finish the aggregation because it doesn't, information for a particular job and cell might not be on a single leaf. It may be spread on more leaves. But each leaf can do as much aggregation as possible. That gets sent up to the zone mixer, which does the final aggregation. We know that can be done because Borg cells don't cross zones, and we get a percentile out. We get the stream of distributions out. We can take the percentile of that, and that gets sent up to the root mixer, which has nothing to do but interleave all of the data. This is an example of the kind of query that would be run purely in the zones from the periodic evaluators. If the aggregation was over just the job and didn't have the Borg cell in it, then the aggregation would continue on the root mixer. It would do the percentile, and you'd have the kind of query that is executed globally. Okay, there are various ways that you use this system. There's a very nice graphical front end. There's a very, then there's also a Python way of doing it for Python. The graphical is very nice for getting started. You can very quickly say, here's what I want you to collect, and Monarch will get started collecting for your thing. You can You can then give ad hoc, make queries, explore your data, and then you can set up alerts and set up consoles. The same thing can be done in Python. That's very important for larger teams or more complex monitoring situations where you really want to have the kind of source code control and whatnot for your configurations. A very important part of this is Monarch as a platform. So having built all of this, you have a solution for people, or you have a tool for people to do monitoring, and it makes it a lot easier for them to set up and get monitoring going. But it isn't a solution to their monitoring problems in and of itself. So listening to the presentations here this week, you hear two kinds of problems. You have the, how do I set up my monitoring and get all of the pieces together and make monitoring actually work? And then there's the, well, what do I look at? How do I condition it for display? How do I do alerts? How do I avoid alert fatigue? Monarch basically addresses the first part. It makes the second part easier, but it's the first part that it's doing. And it's very important that you do this as a platform so that people can come along and build solutions for the second part and build it on that platform for many people to use. And there's a whole host of projects that have grown up in Google around doing this having that kind of very flexible platform has made possible. And I'm not going to read this list because I'm clearly out of time. And I should not forget a very important thing that's built on this platform, which is Google Stackdriver, which is our cloud offering for doing monitoring. Monarch is doing the monitoring of customer instances and resources, as well as the Google services that those customers or resources are using. And this took a good deal of development in the Monarch team, particularly to deal with privacy issues and access control issues, and also different ways of naming things and doing things that are customary in the outside world. And having a very flexible querying mechanism made it possible to support that kind of thing. Okay, did we learn anything from this? One, services looks like the right idea. Being able to get people up and going, to give them global visibility into all of Google, including the things that they're doing and the things that they depend on, is very valuable. Collect and store locally, control, query globally, works. Those were important lessons we learned about this. Building something like this is hard, resource management is hard, user isolation, being robust, so kind of welcome to running a service. But doing that, we've unloaded the work of hundreds of teams within Google who are having to do that basically themselves one at a time. But monitoring is still complex. What you want to look at, how you want to alert, all of those things still need to be solved. This is a very, very powerful tool for solving them, but it isn't a complete solution. And you can't really make one size fits all. So it really has to be a very powerful and general thing, but not necessarily the specific solution people is looking for. So it's very important to have partnerships, to get people, to make the service be a platform so that people can come and address those problems of specific monitoring problems in a way that is useful to a large number of other people. It's a very different focus making a very general purpose monitoring tool like Monarch and crafting solutions that make monitoring straightforward and easy. And it's important that the people doing the first thing provide a platform to the people who are focusing on the second thing. So those are the lessons we learned. And I think I'm out of time. I want to thank you for listening to me. Thank you for staying to the end. And I guess I don't have time for questions, do I? Okay, I'll be on the Slack channel if anyone has questions. All right.
Thank you, John. Thank you to all of our speakers. Thank you to you, and I would like to bring out Jason.
Can we get the stand? Yeah, if you don't mind. As a close friend, Mr. Cheslock might say, hello. I hear one faint laughter out there. Hey, look at that, it worked. All right. Hi, everybody. Still a strong turnout for 5 o'clock on a Wednesday afternoon. I appreciate it. I hope the content was worth it. I'm sure it was, or you wouldn't still be here. But yeah, thank you very much. This has been a fantastic event. I would say that my expectations were exceeded, which are already pretty high just because of the audience and the speakers that we tend to attract here. But I would say it was a very consistently high and level, as far as the content over the 3 days. Some quick thank yous. I wanted to, first of all, this is obvious, but thank you to Will, our assistant organizer and MC extraordinaire, and to all of our volunteers. Please go ahead and clap. It was awesome. Also, thank you to all of our volunteers. Molly Danielle from Heavy Water, Ryan and Ryan, Jennifer Davis. Jennifer did a lot of work helping out with the diversity plans, I guess is the best way to put it, but also her work with the Women's Breakfast, and to my old friend Brad Lotsky. To the video team from Searle Video. I don't know if anybody tried to catch the live stream. I don't know if anybody knows the history of the live stream from Monitorama. Okay, I think you do. Basically in-house with me and my little HDMI consumer camera with a tripod in the back of the audience, trying to, basically the same laptop. Yeah, and for the most part it worked, but a lot of times it didn't. But these guys were consummate professionals. They did a great job. Yeah, so thank you to Paul Searle and his team. To the internet and Wi-Fi team at Step House, they've, we I say, you buy more, and generally speaking, your attendees are going to consume it. I would say there were a couple times where you'd hop between access points, and it felt a little weird. But when you're connected, it was pretty fast and stable this week. So I was really happy with that. And to the immensely professional and highly skilled staff of Portland Center Stage. I don't know if any of them are in here right now, but a big applause for this team. Between Will and everyone else I mentioned and Portland Center Stage, they make me look like a smart guy. Honestly, we couldn't do it without everybody's help and cooperation here. Thumbs up to the back, AV booth. Just great work, as always. And to our sponsors who continue to support us every year, thank you very much. To our speakers who provide us with consistently excellent content every single event. And to all of our attendees, all of you out there who make Monitorama an event that I'm personally proud to ship every year. So thank you for that. Okay, I'm going to assume the other reason why you're still here is because we tend to have some giveaways at the end of the week. And so I don't know if you've seen this kind of floating around. We've had some for the speakers, and because we're ordering from Timbuktu's corporate line, we have to actually have a minimum order. So we happen to have a few left over. And so I'd like to go ahead and give these away if anybody wants to stick around for them. Okay, all right. Now, because we're probably at about 60% capacity right now, there's probably going to be a few misses in here. Can you help with the class? All right, everybody got their tickets out? Back your badge. All right, I'll give you 10 seconds. You already got your paddle. All right,